Nothing in the universe stands still. Not one atom, not one star, not one galaxy in the entire observable cosmos. Everything spins. The planet beneath you is rotating at over 1,000 miles per hour. The sun drags you around its orbit at 67,000 miles per hour. The Milky Way itself is wheeling through space, carrying billions of stars in a dance that takes 200 million years to complete. And deep in the quantum foam, particles too small to ever be seen possess a property called spin, a kind of rotation baked into their very existence, even when they have nowhere to rotate and nothing to rotate through. This is not a coincidence. This is not an accident of physics that happens to show up everywhere we look. This is a law, a commandment written into the fabric of reality 13.8 billion years ago, in the first violent moments after the Big Bang. The universe was born spinning, and it has never stopped. But here is what almost no one asks. Why? Why is stillness forbidden? Why does every collapsing gas cloud spin faster as it falls inward? Why do black holes twist space-time itself into spirals at nearly the speed of light? And why, in a cosmos governed by entropy and decay, does this one property, angular momentum, refuse to die? The answer is not just beautiful, it is essential. Without rotation, galaxies would not form, stars would not ignite, planets would not orbit, you would not exist. The number 10 to the 49th kilograms times meters squared per second is not just a measurement, it is the invisible hand that holds reality together. And this is the story of why the universe cannot afford to sit still. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Everything in the universe is spinning. Right now, the chair you're sitting in is spinning. You are spinning. The floor beneath you, the building around you, the ground under that building, all of it is rotating at roughly 1,000 miles per hour because the Earth is spinning. The Earth is also orbiting the Sun at about 67,000 miles per hour. The Sun is orbiting the center of the Milky Way galaxy at roughly 514,000 miles per hour, dragging the entire solar system along with it. The Milky Way itself is rotating, a massive spiral pinwheel of stars and gas wheeling through space at hundreds of kilometers per second. And the Milky Way is also falling toward the Andromeda Galaxy, and both of them are part of a larger cluster of galaxies that is itself in motion. Nothing sits still, nothing ever has. From the smallest particles to the largest structures in the cosmos, everything moves, and almost all of that motion involves rotation. Spin is baked into the universe at every scale. So the question isn't whether things spin, the question is why. Why does everything rotate? Why doesn't anything just sit there? Why, in a universe that could in theory have been perfectly static, is motion the rule and stillness the exception? The answer goes back to the very beginning, to a moment roughly 13.8 billion years ago when the universe itself began. And depending on how you interpret the physics, it might have been born spinning. Let's start with what we know. The universe is about 13.799 billion years old, give or take 21 million years. That number comes from decades of observations of the cosmic microwave background, the faint glow of radiation left over from when the universe was still young and hot. For most of human history, people assumed the universe was eternal, unchanging, a fixed backdrop against which stars moved. That idea held until the early 20th century when Edwin Hubble pointed his telescope at distant galaxies and noticed something strange. They were all moving away from us. Not just a few of them, all of them. And the farther away a galaxy was, the faster it was receding. That observation led to one of the most disorienting realizations in the history of science. The universe is expanding. Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. And if the universe is expanding now, that means it was smaller in the past. Wind the clock backward far enough and everything, all the matter, all the energy, all the space that exists today, was once compressed into a single, unimaginably dense point. That point exploded. We call it the Big Bang, though the name is misleading. It wasn't an explosion in space, it was an explosion of space, and time, and energy, and everything else, The first fraction of a second after the Big Bang is still mostly a mystery. Physics breaks down at those temperatures and densities. But by the time the universe was about 1/trillionth of a trillionth of a trillionth of a second old, something bizarre happened. The universe underwent a period of cosmic inflation, a sudden burst of expansion so violent and so fast that space itself grew faster than the speed of light. That's not a typo. The expansion of space is not bound by the speed limit that governs particles moving through space. During inflation, the universe doubled in size over and over again, dozens of times in a span shorter than a blink. By the time inflation ended, a region smaller than a proton had ballooned to something the size of a grapefruit, and all the energy that had been driving that expansion was dumped back into the universe as matter and light. That's where everything came from. The energy of inflation became particles, which became atoms, which became stars, planets, and eventually people. About 1 second after the Big Bang, the universe was still unimaginably hot, something like 10 billion degrees Celsius. At that temperature, matter couldn't hold together in any form we would recognize. There were no atoms, no molecules, just a seething soup of quarks, electrons, photons, and other particles smashing into each other at near light speed. Over the next few minutes, as the universe expanded and cooled, the quarks began to stick together, forming protons and neutrons. Those protons and neutrons collided and fused, building the first atomic nuclei. By the time the universe was about 5 minutes old, most of the hydrogen and helium that exists today had already been forged. Trace amounts of lithium and beryllium formed as well, but that was it. The universe was too cool for any heavier elements to form. Carbon, oxygen, iron, everything else would have to wait for stars. For the next 380,000 years, the universe remained opaque. It was still too hot for electrons to stick to nuclei and form stable atoms. Photons couldn't travel more than a short distance before smacking into a free electron and scattering in a different direction. The universe was a glowing fog. Then, at around 380,000 years, the temperature finally dropped enough for electrons to combine with nuclei. Hydrogen atoms formed, helium atoms formed, and suddenly, for the first time, the universe became transparent. Light could travel freely. The glow from that moment has been travelling through space ever since. We call it the cosmic microwave background, the oldest light we can observe. NASA describes it plainly. The universe became transparent. That faint radiation, stretched and cooled by 13.8 billion years of expansion, is still detectable today as a faint microwave hum coming from every direction in the sky. It's the afterglow of creation, and it's one of the most important pieces of evidence we have for the Big Bang itself. After the cosmic microwave background was released, the universe went dark. There were no stars yet, no galaxies, just vast clouds of hydrogen and helium drifting through empty space. For roughly the next 200 million years, the universe was a cold, dark void. Astronomers call this period the Cosmic Dark Ages, and it's one of the least understood chapters in the history of the cosmos. We can't see it directly, there was no light, but we know what happened during that time because we can see what came after. Gravity was at work. Tiny fluctuations in the density of matter, quantum ripples that had been stretched to cosmic scales during inflation, began to pull gas together. Denser regions attracted more gas. Those regions grew denser still. Slowly, over millions of years, the first structures began to form. Clouds of hydrogen and helium collapsed under their own weight, heating up as they shrank. Eventually, the cores of those clouds became hot enough to ignite nuclear fusion. The first stars lit up. From there, things moved faster. Stars clustered together into the first galaxies. Galaxies collided and merged. Larger structures formed, and everywhere, at every scale, things were spinning. This is where the mystery deepens, because nothing in the standard story of the Big Bang requires the universe to have rotation. Expansion, yes. Structure formation, yes. But spin, that's not a necessary ingredient. In fact, for a long time, cosmologists assumed the early universe had no net rotation at all. The Big Bang was supposed to be perfectly symmetric, expanding uniformly in all directions. And yet, when we look at the universe today, we see rotation everywhere. Every planet spins, every star spins, every galaxy spins, even black holes spin. The universe is full of angular momentum and no one can fully explain where it all came from. Angular momentum is a measure of rotational motion. It depends on three things: how much mass is moving, how fast it's moving, and how far that mass is from the centre of rotation. A spinning ice skater has angular momentum. Pull your arms in and you spin faster because you've moved mass closer to the centre. The total angular momentum stays the same, but the rotation speeds up. That's conservation of angular momentum, one of the most fundamental laws in physics. If no external force acts on a system, its angular momentum cannot change. That rule applies to ice skaters, hurricanes, galaxies, and as far as we can tell, the entire universe. So if the universe has angular momentum now, it must have had angular momentum from the start. That's what conservation demands. But the Big Bang itself doesn't automatically produce rotation. Expansion is not the same as spin. Imagine blowing up a balloon. The surface stretches uniformly in all directions. That's expansion. Now imagine trying to twist the balloon while it's inflating. That's rotation. The two are different, and while the Big Bang gave us expansion, there's no obvious mechanism in the standard model that gives us rotation. And yet, here we are, living on a spinning planet, orbiting a spinning star, inside a spinning galaxy, in a universe where stillness is nowhere to be found. The leading theory for how angular momentum entered the universe involves something called tidal torques. During the cosmic dark ages, when the first structures were forming, the distribution of matter was not perfectly smooth. There were denser clumps and emptier voids. As those clumps pulled on each other gravitationally, they didn't just attract. They tugged unevenly. A cloud of gas collapsing toward a dense region might be pulled a little harder on one side than the other, because a neighbouring clump was exerting its own gravitational pull. That uneven tug would cause the cloud to twist as it collapsed. Over time, that twist became rotation. The process is subtle, but it's powerful. Every irregularity in the early universe, every tiny fluctuation in density, had the potential to generate spin. And because the universe was full of irregularities, spin became universal. The gas clouds that would eventually become galaxies started rotating before they even had stars. The material that would later collapse into the solar system was already spinning billions of years before the sun ignited. There's another mechanism that might have contributed, though it's more speculative: turbulence. In a collapsing gas cloud, material doesn't fall inward smoothly. It clumps, swirls, and churns. Think of water draining out of a bathtub. The flow isn't uniform, it spirals. Gas clouds in the early universe might have behaved the same way. As they collapsed under gravity, turbulence could have generated eddies and vortices, regions where the gas was swirling faster than the surrounding material. Over millions of years, those eddies could have merged and organized into large-scale rotation. The chaotic motion of the early universe, in other words, might have sorted itself into spin. Dark matter complicates the picture. Dark matter makes up about 85% of the matter in the universe, but it doesn't emit light, and it doesn't interact with ordinary matter except through gravity. We know it's there because we can see its gravitational effects on galaxies and galaxy clusters, but we've never directly detected a dark matter particle. In the early universe, dark matter formed halos, vast invisible clouds that pulled ordinary matter toward them. Those halos were the scaffolding on which galaxies were built, and because dark matter itself was subject to the same gravitational instabilities that affected normal matter, those halos were probably spinning too. When hydrogen and helium gas fell into a dark matter halo, it brought its own angular momentum with it. The halo's rotation influenced the gas. The gas's rotation influenced the halo. Over time, the two locked together, and the resulting structure, a spinning cloud of dark matter and gas, became the birthplace of a galaxy. None of this was planned. There was no cosmic architect deciding which clouds should spin and which direction they should spin in. The rotation was a byproduct of gravity acting on an imperfect universe, but once it started, it never stopped. Conservation of angular momentum guaranteed that. A cloud of gas with even a tiny amount of spin will rotate faster as it collapses, just like the ice skater pulling in her arms. By the time the first stars formed, the clouds they were born from were already spinning rapidly. By the time galaxies assembled, they were rotating fast enough to flatten into disks. The spiral arms we see in galaxies like the Milky Way are the direct result of that rotation, density waves rippling through a spinning disk of stars and gas. It's worth pausing to appreciate how strange this is. The universe did not have to be this way. In principle, the Big Bang could have produced a universe where everything just expanded outward in straight lines. No spin, no orbits, no galaxies shaped like pinwheels, just a uniform, boring scattering of matter drifting apart forever. That's not the universe we got. We got a universe where motion is the default, where rotation is written into the structure of reality at every scale. And the reason seems to be that the early universe was lumpy. Not perfectly smooth, not perfectly symmetric, just slightly irregular. And those irregularities, amplified by gravity over billions of years, gave us a cosmos in motion. There's one more piece to this puzzle, and it's the most unsettling. We don't actually know if the universe as a whole is rotating. Galaxies spin, galaxy clusters spin. But does the entire universe have a net angular momentum? Is there some cosmic axis around which everything is turning? For most of the 20th century, the answer was assumed to be no. The cosmological principle, one of the guiding assumptions of modern cosmology, states that the universe is homogeneous and isotropic. That's a fancy way of saying it looks the same in all directions and at all locations. If the universe were rotating, there would be a preferred direction, an axis of spin, and the cosmological principle would be violated. So most cosmologists ruled it out. The universe, they said, expands but does not rotate. Then, in the 1990s and 2000s, a few research teams started analysing the cosmic microwave background more carefully. They were looking for patterns, subtle asymmetries in the temperature and polarisation of the radiation, and they found something odd. The microwave background is not perfectly uniform. There are tiny fluctuations, hot spots and cold spots, that reflect the density variations in the early universe. Most of those fluctuations are random, as expected, but a few statistical analyses suggested there might be a slight alignment, a hint of a preferred direction in the data. Some researchers interpreted that as evidence of cosmic rotation. Others argued it was just noise, a statistical fluke amplified by the human tendency to see patterns where none exist. The debate is still unresolved. If the universe is rotating, the effect is tiny, far below what current instruments can definitively measure. But the possibility remains open, and if future observations confirm it, we'll have to rewrite the cosmological principle and rethink the symmetry of the Big Bang itself. For now, what we can say with confidence is that the universe is full of spin. From the moment the first gas clouds began to collapse, rotation became a permanent feature of cosmic structure. Angular momentum once created is never destroyed, it only redistributes. A spinning cloud collapses into a spinning disk. A spinning disk fragments into spinning clumps. Those clumps become spinning stars, spinning planets, spinning moons. At every stage, the spin is passed down like an inheritance. The Earth's rotation, the orbit of the Moon, the spiral arms of the Milky Way, all of it traces back to the irregular collapse of matter in the first few 100 million years after the Big Bang. We are living inside the consequences of turbulence that happened when the universe was less than 1% of its current age. And here's the thing, none of it had to happen. The laws of physics don't require rotation. Conservation of angular momentum only says that if you have spin, you keep it. It doesn't explain where the spin came from in the first place. The best answer we have is that the early universe was messy. Gravity acted on imperfect clouds of gas. Tidal forces twisted them. Turbulence stirred them. And out of that chaos came order. Rotating disks, orbiting planets, spinning stars. The universe didn't start with a plan, it started with noise. And noise, it turns out, is enough. This is the foundation, the cosmic genesis of motion. A universe born not in perfect stillness, but in motion, in collapse, in spin. Everything that followed, every structure, every galaxy, every star, emerged from clouds of gas that were already rotating before the first light ever flickered. The spin was there from the beginning, woven into the fabric of the cosmos by the gravitational chaos of the early universe. And once it began, it never stopped. Because in a universe governed by conservation laws, motion is permanent. Spin, once started, cannot be undone. It can only be transformed, redistributed, passed along. From collapsing gas clouds to spinning galaxies to rotating planets, to the chair you're sitting in right now, the motion is unbroken. A thread connecting every rotating object in the universe back to the same source. The lumpy, chaotic, imperfect collapse of the first structures in the cosmic dark ages. That's where the spin came from. That's where it all began. And the universe has been spinning ever since. The universe has rules, not the kind printed in textbooks or etched on tablets, the kind that cannot be broken, bent, or negotiated with, the kind that were true before the first star ignited and will remain true long after the last one dies. One of those rules governs rotation, and it has shaped every spinning object that has ever existed. Conservation of angular momentum. 4 words that contain the entire reason why everything in the cosmos moves the way it does. Angular momentum is a measure of how much spin a system has. It's not just speed, it's not just mass, it's both, combined with how far that mass is distributed from the center. The formula is simple. Angular momentum equals moment of inertia times angular velocity. In plain language, that's how spread out the mass is, multiplied by how fast it's rotating. Change one side of that equation, and the other side has to change to keep the total the same. That's conservation. The total spin of a system cannot increase or decrease unless something external pushes on it. And in the vast empty reaches of space, there's usually nothing around to push. This law is why ice skaters spin faster when they pull their arms in. The skater's mass doesn't change. The total angular momentum doesn't change. But by pulling mass closer to the axis of rotation, the skater decreases the moment of inertia. And if angular momentum equals moment of inertia times angular velocity, and angular momentum has to stay constant, then angular velocity has to increase. The skater spins faster, not because they pushed off the ice, not because they tried harder, because the universe demanded it. Conservation of angular momentum is not a suggestion, it's enforcement. Now scale that up. Take a cloud of gas and dust floating in space, light years across, drifting through the void between stars. The cloud is massive, maybe a few thousand times the mass of our sun, but it's spread out. Diffuse. The density is lower than the best vacuum we can create on Earth. If you were standing inside it, you wouldn't see a cloud. You'd see darkness with maybe a faint haze if you looked hard enough. The cloud is also rotating, but slowly. So slowly that one full rotation might take millions of years. At that scale, with mass distributed over such a huge volume, the moment of inertia is enormous, and because angular momentum equals moment of inertia times angular velocity, a large moment of inertia means the angular velocity can be tiny, and the cloud still has plenty of spin. It's rotating, just barely, drifting through space like a slow-motion whirlpool light years wide. Then gravity wakes up. Some disturbance, maybe a nearby supernova shockwave, maybe the gravitational tug of a passing star, compresses part of the cloud just enough to tip it past a threshold. The denser region pulls on the surrounding gas. The gas falls inward. The cloud begins to collapse. This is where the invisible hand of the cosmos tightens its grip. As the cloud contracts, the moment of inertia decreases. Mass that was once spread across light years is now confined to a smaller and smaller volume. And because angular momentum must be conserved, because the universe does not allow that number to change without an external force, the angular velocity increases. The cloud spins faster. Not by choice, not because anything pushed it, because the math demands it. At first, the change is subtle. A cloud that was rotating once every few million years might speed up to once every 100,000 years, barely noticeable, but gravity doesn't stop. The collapse continues. The cloud shrinks further. The moment of inertia drops further. The spin accelerates further. Feedback kicks in. The faster the cloud spins, the more it resists collapsing in certain directions. Material falling toward the center, along the axis of rotation, can fall almost unimpeded. But material trying to fall inward, perpendicular to that axis, gets flung outward by centrifugal force. The cloud begins to flatten. What was once a roughly spherical blob of gas starts to take on a new shape, a disk. The material settles into a plane, orbiting the center in a coordinated swirl. This is how protoplanetary disks form, not because gas likes to form disks, because rotation and gravity, acting together under the constraint of angular momentum conservation, force the gas into that shape. The disk is not a choice, it's a consequence, and once the disk forms, the collapse accelerates further. Now the cloud's mass is concentrated in a thin plane instead of a sphere. The moment of inertia along the axis of rotation drops dramatically. The spin speeds up even more. What started as a lazy drift becomes a furious vortex. A cloud that once took millions of years to complete a rotation might now spin once every few thousand years, then every few hundred, then faster still. This process is happening right now in star-forming regions scattered across the galaxy. The Orion Nebula, one of the closest stellar nurseries to Earth, is full of collapsing gas clouds in various stages of this transformation. Some are still large and diffuse. Others have already flattened into tight disks with dense cores at their centres. In a few million years, those cores will ignite as new stars. The disks around them will fragment into planets, and all of it will be spinning, every piece of it, because the original cloud was spinning, and conservation of angular momentum does not allow that spin to vanish. The numbers involved are staggering. A typical molecular cloud might start with a rotation period of 10 million years. By the time it collapses into a protostar surrounded by a disk, the rotation period might be a few thousand years. By the time planets form in that disk, some of them will be rotating once every few hours. Earth completes a full rotation in 24 hours. Jupiter does it in less than 10. That acceleration from millions of years per rotation to hours per rotation is not gradual, it's exponential, and it's all driven by one equation. Angular momentum equals moment of inertia times angular velocity. Shrink the size, speed up the spin, every time, without exception. There's a useful analogy here, though it's not perfect. Imagine a crowded cafeteria. People are milling around, drifting slowly, no real pattern. Someone near the centre drops something valuable, maybe a wallet. A few people notice and start moving toward it. Others see the motion and follow. Within seconds, everyone is converging on the centre. But the cafeteria has doors on opposite sides, and people entering from one door are moving slightly to the left, while people from the other door are moving slightly to the right. As the crowd compresses toward the centre, that slight sideways drift becomes a noticeable swirl. The tighter the crowd packs, the faster the swirl becomes. People who are barely moving sideways at the edge of the room are now circling the centre rapidly, caught in a vortex they didn't intend to create. That's angular momentum conservation in a cafeteria. The same principle governs collapsing gas clouds, just on a scale millions of times larger. But the cafeteria analogy breaks down in one important way. People can push against each other. They can stop, turn around, resist the flow. Gas clouds can't. Once gravity starts pulling a cloud inward, there's no friction to slow it down in the traditional sense. The only thing resisting collapse is pressure, the outward push from the gas heating up as it compresses, and in the early stages of collapse that pressure is weak. Gravity wins, the cloud contracts, the spin accelerates, and the universe simply watches, enforcing its rules without comment. Magnetic fields complicate the picture. Gas clouds in space are not electrically neutral. They contain ions, charged particles that respond to magnetic fields threading through the cloud. As the cloud collapses, those magnetic field lines get dragged inward with the gas, but they also resist being compressed. Magnetic fields exert pressure. They push back against the collapse, especially in directions perpendicular to the field lines. More importantly, magnetic fields can transfer angular momentum. A charged particle spiraling around a magnetic field line is coupled to that line. If the particle tries to move inward, the field line resists. If the particle spins faster, the field line can carry some of that rotational energy outward to other parts of the cloud. This process is called magnetic braking, and it's one of the few mechanisms that can actually slow down the spin of a collapsing cloud without violating conservation of angular momentum. The angular momentum isn't destroyed, it's just moved, transferred from the dense inner region to the more diffuse outer layers. The core spins slower than it otherwise would. The outer envelope spins slightly faster. The total angular momentum stays the same. Magnetic braking is critical in star formation. Without it, collapsing clouds would spin up so fast that centrifugal force would tear them apart before they could form a star. The math is unforgiving. A typical molecular cloud has enough angular momentum that if all of it stayed in the collapsing core, the core would be spinning fast enough to fly apart long before reaching the temperatures needed for nuclear fusion. Stars would never form. Planets would never form. We wouldn't be here. Magnetic fields save the process by siphoning off some of that angular momentum, slowing the core's rotation just enough to let gravity finish the job. The star forms. The leftover material settles into a disk, and the disk, still spinning rapidly, becomes the birthplace of planets. Turbulence adds another layer. Gas clouds are not smooth, laminar flows, they're chaotic, supersonic winds, shock waves from nearby supernovae, and instabilities in the gas itself create eddies and vortices at every scale. Some of those eddies reinforce the cloud's overall rotation, others oppose it. When two eddies collide, they can merge, transferring angular momentum between them. Over time, turbulence redistributes spin throughout the cloud in ways that are difficult to predict. In some regions, the spin concentrates, in others, it dissipates. The result is that different parts of the cloud end up with different rotation rates, and those differences persist even after the cloud collapses. This is why planets in the same solar system can have wildly different rotation periods. Earth spins once every 24 hours. Venus takes 243 days. Mercury is locked in a 3-2 resonance with the Sun. They all formed from the same spinning disk, but turbulence and subsequent interactions redistributed the angular momentum unevenly. The formation of a protoplanetary disk is one of the most beautiful consequences of angular momentum conservation, and it happens in stages. Stage 1 is the initial collapse. The cloud contracts under gravity. Rotation speeds up. The cloud flattens slightly, but it's still mostly spherical. Stage 2 begins when the central core becomes dense enough to resist further collapse. Pressure builds up. The core heats up. Material can no longer fall straight inward. Instead, it spirals. The infalling gas carries angular momentum with it, and that angular momentum has to go somewhere. It can't just disappear. So the gas spreads out into a rotating disk around the core, orbiting in a plane perpendicular to the axis of rotation. Stage 3 is disk evolution. The disk is not static. Material in the disk slowly spirals inward toward the core, but as it does, it transfers angular momentum outward to the rest of the disk. The inner regions lose spin and fall inward. The outer regions gain spin and drift outward. Over millions of years, the disk spreads, and the core grows, fed by the steady inflow of gas from the disk. Eventually, the core becomes massive enough and hot enough to ignite fusion. A star is born. The disk remains, now called a protoplanetary disk, and within it, dust grains collide, stick together, and grow into larger and larger bodies. Those bodies become planets. Every step of this process is governed by angular momentum conservation. The disk can't collapse directly onto the star because it's spinning too fast. The material has to lose angular momentum first, and the only way to do that is to transfer it outward to other material in the disk. So the disk becomes an engine for redistributing spin. Matter moves inward. Angular momentum moves outward. The star grows. The disk spreads. And the planets form in the space between. All of it driven by a single rule. Angular momentum cannot be created or destroyed. It can only be moved around. There's a second analogy that might help, though like the cafeteria, it's imperfect. Imagine a merry-go-round, a large, slowly spinning merry-go-round with people standing at the edge. The ride is massive, the rotation is lazy, and the moment of inertia is huge. Now imagine the people start walking toward the center. As they move inward, the moment of inertia decreases. The merry-go-round spins faster, assuming no external force slows it down. If the people keep moving toward the center, the spin keeps accelerating. The closer they get to the center, the faster the ride spins. Eventually, if they get close enough, the centrifugal force becomes so strong that they can't move any closer without being flung outward. So they stop at some intermediate distance and start circling the center in a coordinated orbit. That's the disk. That's the stage where planets form. The material has spiraled inward as far as angular momentum will allow, and now it's stuck in orbit, unable to fall further without first shedding spin. The role of viscosity in the disk is subtle but important. In a perfectly frictionless disk, material would just orbit forever. Nothing would ever fall inward. The disk would be stable, unchanging. But real disks have viscosity, a kind of internal friction caused by turbulence and magnetic fields. Viscosity allows adjacent rings of material in the disk to transfer angular momentum between them. A faster spinning inner ring can transfer some of its spin to a slower spinning outer ring. When that happens, the inner ring loses angular momentum and spirals inward. The outer ring gains angular momentum and drifts outward. Over time, this process drains material from the disk onto the star while simultaneously spreading the disk outward. It's a slow process, taking millions of years, but it's relentless. And it's all driven by angular momentum conservation. The disk can't collapse onto the star without getting rid of its spin first, and viscosity provides the mechanism to do that. Observations confirm all of this. In the last few decades, astronomers have imaged dozens of protoplanetary disks around young stars using telescopes like ALMA, the Atacama Large Millimeter Array. Those images show exactly what the theory predicts. Flat disks of gas and dust rotating around central stars, gaps in the disks where planets are likely forming, spiral arms where material is piling up, asymmetries caused by turbulence and magnetic fields. The disks are not smooth, they're structured, layered, dynamic. And every feature we see can be traced back to angular momentum conservation combined with gravity, pressure, and magnetic forces. The universe is running a physics simulation in real time, and we're watching the results. One of the most striking examples is HL Tauri, a young star about 450 light-years from Earth. In 2014, ALMA captured an image of the disk around HL Tauri in such detail that astronomers could see individual rings and gaps. The gaps are almost certainly carved out by newly forming planets, bodies massive enough to gravitationally clear their orbital paths. The star itself is less than 1 million years old. The disk is still in the process of forming planets, and we're seeing it happen. The rings in the disk are zones where material has piled up, regions where angular momentum is temporarily concentrated. The gaps are zones where material has been cleared away, either accreted onto a planet or pushed outward. The entire structure is a direct consequence of angular momentum being redistributed by gravity and friction. The disk is an engine, processing gas and dust and turning it into planets, all while conserving the total spin of the system. The process isn't perfectly efficient. Some angular momentum escapes. Jets of gas shoot out from the poles of young stars, carrying material and spin away from the system. These jets are driven by magnetic fields threading through the disk, and they're one of the few ways a star can actually lose angular momentum during formation. The jets are fast, often moving at hundreds of kilometers per second, and they can extend for light years. As the jets carry gas away, they carry angular momentum with them, allowing the core of the collapsing cloud to spin down just enough to avoid flying apart. The total angular momentum of the cloud, star, disk, and jets combined is still conserved. It's just spread out over a much larger volume. There's a deeper point here that's easy to miss. Angular momentum conservation isn't just a detail in the story of how stars and planets form, it's the main character. Gravity provides the pull, pressure provides the resistance, magnetic fields and turbulence provide the complexity. But angular momentum conservation is the rule that determines what shape the final structure takes. Without it, collapsing clouds would just shrink into points. With it, they flatten into disks. Without it, planets would never form. Material would just spiral into the star. With it, planets form in stable orbits, their positions determined by where angular momentum allowed them to settle. The rule is invisible. You can't see it. You can't touch it. But its consequences are everywhere. Every rotating object in the universe is a testament to conservation. Every orbit, every spin, every disk of gas swirling around a young star, all of it shaped by a law that has no exceptions. And here's the eerie part. The law doesn't care. It doesn't know what it's creating. It doesn't have a goal. It's just math, a relationship between mass, distance, and rotation rate. But that relationship, enforced without exception across billions of years, has built every structure in the cosmos. Galaxies, stars, planets, moons. Even the rings around Saturn are a consequence of angular momentum conservation. Material orbiting the planet, unable to fall inward because it's spinning too fast, unable to escape because gravity holds it in place. The rings are frozen in a balance dictated by spin. They've been there for hundreds of millions of years, maybe longer, and they'll stay there until something disrupts the balance. But as long as the system is left alone, as long as no external force acts on it, the rings will keep spinning, because that's what conservation demands. The cafeteria analogy and the merry-go-round analogy both try to capture this idea, but they both fail in one crucial way. People can resist, they can push back, they can decide to stop. Gas clouds can't, planets can't, stars can't. Once the spin is there, once the angular momentum is established, the system has no choice but to obey. Shrink the size, spin faster, spread the mass, spin slower, transfer the momentum, change the distribution, but the total never changes unless something external intervenes. And in the vast empty spaces between stars, external intervention is rare, so the spin persists, generation after generation, cloud to disk to star to planet. The angular momentum set in motion billions of years ago in the chaotic turbulence of the early universe is still here, still conserved, still shaping the motion of everything we see. This is the invisible hand, not a force in the traditional sense, not something you can point a detector at and measure directly, but a constraint, a rule, an unyielding fact about how the universe works. Angular momentum conservation is the reason collapsing clouds spin faster. It's the reason protoplanetary disks form. It's the reason planets orbit stars instead of falling into them. It's the reason galaxies are flat spirals instead of spherical blobs. And it's the reason, ultimately, that we live on a spinning planet circling a spinning star in a spinning galaxy. The spin was always there. Gravity concentrated it. Conservation amplified it. And the result is a universe in motion, where stillness is forbidden and rotation is the rule. Every star, every planet, every moon, every galaxy, all of them spinning, all of them obeying the same invisible law. And from that law, from that one simple equation, angular momentum equals moment of inertia times angular velocity, the entire cosmic dance was born. We've talked about clouds collapsing, about conservation laws that don't bend, about angular momentum being passed down through billions of years like an inheritance no one can refuse. Now we need to see what that actually builds, because the abstract rules of physics are fine in a textbook, but out in the real universe those rules are building stars, planets, entire solar systems, and they're doing it on a scale that should make you uncomfortable. The dance of giants. Stars and planets locked in an eternal whirl, not because they want to, because the math left them no other option. Let's start with a star being born. Not our sun, though the process is the same. Picture a cloud of gas and dust somewhere in the Orion Nebula, about 1300 light-years from Earth. The cloud is cold, maybe 10 or 20 degrees above absolute zero. It's massive, a few times the mass of our sun, but spread across a volume so large that if you were floating in the middle of it, you'd see almost nothing. Just darkness, with maybe a faint haze if your eyes had time to adjust. The cloud has been drifting for millions of years, part of a larger nebula, a stellar nursery where dozens of other clouds are also collapsing into stars. This particular cloud hasn't started collapsing yet. It's in equilibrium. Gravity is pulling inward, but pressure and turbulence are pushing outward, and the forces are balanced. The cloud is rotating very slowly, maybe one full turn every few million years. That rotation is so slow that calling it spin feels generous. It's more like a lazy drift. But it's there, a tiny bit of angular momentum spread across a volume light-years wide. Then something tips the balance. Maybe a shockwave from a nearby supernova passes through the region, compressing part of the cloud just enough. Maybe a dense clump of gas from another cloud collides with this one. Maybe random turbulence inside the cloud creates a region that's slightly denser than the rest. It doesn't matter what the trigger is. Once gravity gets a foothold, it doesn't let go. The dense region pulls on the surrounding gas. Gas falls inward. The region grows denser. Gravity pulls harder. The collapse accelerates. And as the cloud contracts, as the moment of inertia drops, the rotation speeds up. The lazy drift becomes a noticeable spin. The spin becomes a rapid rotation. Within a few 100,000 years, the cloud has shrunk by a factor of 1,000. The rotation period has dropped from millions of years to a few thousand. The cloud is no longer a diffuse blob. It's a flattened disk with a dense bulge at the center, and that bulge is hot. As gas falls inward, it compresses. Compression heats gas the same way pumping air into a tire heats the pump. By the time the core of the collapsing cloud reaches a few thousand degrees, it starts glowing. A protostar is born. Not a real star yet. It's not hot enough for fusion, but it's bright, lit by the heat of its own collapse. At this stage, the protostar is spinning fast, really fast. A rotation period of a few days is common. For comparison, our Sun, a mature star about 5 billion years old, rotates once every 25 days at its equator. Protostars spin 5 or 10 times faster. The reason is simple. The core of the collapsing cloud inherited all the angular momentum from the original diffuse cloud, and that momentum got concentrated into a much smaller volume. Angular momentum equals moment of inertia times angular velocity. Shrink the size, spin speeds up. The protostar has no choice but to obey, and as it continues pulling in gas from the disk around it, it pulls in more angular momentum. In principle, the protostar should spin faster and faster until it tears itself apart. Centrifugal force at the equator becomes so strong that the star can't hold itself together. The outer layers get flung into space. The star never finishes forming. That should happen all the time, except it doesn't. Stars form. They're everywhere. So something must be slowing them down. Magnetic fields. That's the answer. Young stars generate powerful magnetic fields threading through the surrounding disk. Those fields couple to the ionized gas in the disk, and as the gas spirals inward, the magnetic field lines get dragged along. But the field lines also extend outward, far beyond the star, and they're anchored in gas that's still rotating more slowly. The result is that the field acts like a brake. The star tries to spin faster, but the magnetic field connects it to the slower spinning disk. Angular momentum gets transferred outward along the field lines, carried away from the star and deposited in the outer disk. The star spins down. The disk spins up slightly. Over a few million years, the protostar loses enough angular momentum that it can continue collapsing without flying apart. By the time the core reaches 10 million degrees and fusion ignites, the star has settled into a stable rotation period, usually somewhere between a few days and a few weeks depending on its mass. The star is spinning. It will keep spinning for the rest of its life, but it's not spinning so fast that it destroys itself. Magnetic braking saved it. The disk is still there though, a flat swirling plane of gas and dust orbiting the newborn star. And that disk is where planets form, not all at once, not smoothly. The process is violent, chaotic, and takes millions of years. It starts with dust, tiny grains of silicates and carbon compounds, each smaller than the width of a human hair. The grains drift through the disk, colliding with each other at low speeds. Sometimes they stick. Static electricity helps. Van der Waals forces help. The grains clump together into larger grains. Those clumps collide and stick to other clumps. Over thousands of years, the clumps grow into pebbles. Pebbles grow into rocks. Rocks grow into boulders. The boulders start exerting their own gravity, pulling in more material. The process accelerates. Within a few 100,000 years, the disk is full of kilometre-sized bodies called planetesimals. The planetesimals smash into each other. Most of the collisions are destructive. The bodies shatter, sending fragments flying. But some collisions are slow enough that the bodies merge instead of breaking apart. Those mergers build bigger bodies, and bigger bodies have stronger gravity. They start sweeping up everything in their orbital path. After a few million years, a handful of planetesimals have grown massive enough to dominate their regions of the disk. Those are the planetary embryos. Give them another few million years and they'll grow into planets. Every planet that forms inherits angular momentum from the disk. The disk was rotating. The material that built the planet was rotating. The planet has no choice but to rotate as well. But the amount of spin a planet ends up with depends on how it formed, and that's where things get messy. If a planet grows slowly, accreting small particles over millions of years, the collisions average out. Material hits from all directions. The angular momentum from each collision is small and random. The planet ends up with a moderate spin. But if a planet grows through giant impacts, collisions with other planetary embryos the size of Mars or larger, the spin can change dramatically. One large impact can speed up the planet's rotation. Another can slow it down. A third can knock the planet's axis sideways, tilting it at a strange angle. Earth's rotation is the result of this chaotic history. We spin once every 24 hours, and our axis is tilted 23.5 degrees relative to our orbital plane. Both of those numbers are the leftover consequences of collisions that happened more than 4 billion years ago. The most dramatic impact in Earth's history happened roughly 30 to 50 million years after the planet started forming. A Mars-sized body, often called Theia, smashed into the young Earth. The collision was catastrophic. Theia's core merged with Earth's core. The outer layers of both bodies were vaporized and blown into space. Some of that debris fell back onto Earth. The rest formed a ring of molten rock orbiting the planet. Over the next few thousand years, the ring coalesced into the moon. The impact also changed Earth's spin. Before Theia hit, Earth was probably rotating faster, maybe once every 5 or 6 hours. The collision added angular momentum in a specific direction, speeding up the rotation even more at first. Then, over millions of years, tidal forces between Earth and the Moon gradually slowed Earth's rotation down to the 24-hour day we have now. The moon has been stealing angular momentum from Earth's spin and using it to move farther away. The process is still happening. Every year, the moon drifts about 3.8 centimeters farther from Earth. Every century, Earth's day gets about 1.8 milliseconds longer. The numbers are tiny, but they add up. 4 billion years ago, a day on Earth was only about 6 hours long. 4 billion years from now, if Earth is still here, a day will be longer than a month. The moon will be farther away, and both changes are driven by the same mechanism: tidal forces transferring angular momentum between Earth's spin and the moon's orbit. Let's talk about tides, because this is one of the most important and least appreciated ways angular momentum gets redistributed in planetary systems. When you hear the word tide, you probably think of ocean water sloshing back and forth. That's the visible effect. The cause is gravity. The moon pulls on Earth, but the moon's gravity isn't uniform across the planet. The side of Earth facing the moon feels a slightly stronger pull than the centre. The side facing away feels a slightly weaker pull. The difference is small, but it's enough to stretch Earth slightly along the line connecting Earth to the moon. The solid body of the planet deforms by about 30 centimeters. You don't notice it, because the entire planet is deforming together, ground and all. But the oceans are free to flow, and they pile up on the side facing the moon and the side facing away. Those two bulges are the tides. High tide happens when your location rotates into one of the bulges. Low tide happens when you're in between. Now here's the part that matters for spin. Earth is rotating faster than the moon is orbiting. Earth spins once every 24 hours. The moon orbits once every 27.3 days. That means the tidal bulges are trying to stay aligned with the moon, but Earth is rotating underneath them. The bulges get dragged forward by Earth's rotation. Picture the high tide bulge as a lump of water on Earth's surface. The lump is trying to point toward the moon, but Earth's rotation is carrying it ahead of the moon. The lump is now slightly in front of the moon instead of directly underneath it, and because the lump has mass, it has gravity. That gravity pulls on the moon. The pull is tiny, but it's in the direction of the moon's orbit. So the tidal bulge is constantly tugging the moon forward, speeding up its orbit. When you speed up an orbit, the object moves to a higher, more distant orbit. That's why the moon is drifting away. Earth's tidal bulge is pushing it outward. At the same time, the moon's gravity is pulling backward on the tidal bulge, trying to drag it into alignment. That backward pull slows down Earth's rotation. Angular momentum is being transferred from Earth's spin to the moon's orbit. The total angular momentum of the Earth-Moon system stays the same, but over billions of years the distribution has shifted. Earth spins slower. The moon orbits farther out. Both changes are the result of tides. This process doesn't stop. Eventually, billions of years from now, Earth's rotation will slow down enough that one side of the planet always faces the moon. At that point, the tidal bulge will be locked in place, no longer being dragged forward by Earth's rotation. The transfer of angular momentum will stop. Earth and the moon will be tidally locked to each other. Earth will rotate once per month. The moon will orbit once per month. The same face of Earth will always point toward the moon, and the same face of the moon will always point toward Earth. This is called double tidal locking, and it's the inevitable end state of any two-body system left alone long enough. The moon is already tidally locked to Earth. It rotates once every 27.3 days, the same period as its orbit. That's why we always see the same side of the moon. The far side of the moon, often incorrectly called the dark side, isn't dark. It gets just as much sunlight as the near side. We just never see it from Earth because the moon's rotation is synchronized with its orbit. That synchronization didn't happen by accident. It happened because Earth's tidal forces acting on the moon slowed the moon's rotation over billions of years until it matched the orbit. The process is automatic. It's a consequence of tidal friction and angular momentum conservation, and it happens to almost every large moon in the solar system. Tidal locking explains a lot of strange behavior in the solar system. Mercury, the closest planet to the Sun, isn't tidally locked, but it's close. It rotates 3 times for every 2 orbits around the Sun, a 3-to-2 resonance. That's a stable configuration caused by the Sun's tidal forces acting on Mercury's slightly elongated shape. Pluto and its largest moon Charon are doubly tidally locked. Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. The two bodies orbit their common centre of mass, and both their spins are synchronized to that orbit. This is the future waiting for Earth and the Moon, assuming nothing disrupts the system before then. Tidal locking is the universe's way of settling arguments about angular momentum. Spin and orbit can't stay out of sync forever. Tides will gradually transfer momentum between them until they match. It takes billions of years, but the outcome is predictable. Here's where things get more interesting. Not every planet spins the way you'd expect. Venus, the second planet from the Sun, rotates backward. Most planets spin in the same direction they orbit, counterclockwise as seen from above the solar system's north pole. Venus spins clockwise, slowly. One rotation takes 243 Earth days, longer than Venus's year, which is only 225 days. So on Venus, a day is longer than a year, and it's spinning the wrong way. Nobody knows for sure why. The leading theory is that Venus was hit by a massive object early in its history, something large enough to flip its spin axis by more than 90 degrees. Or maybe tidal forces from the Sun acting on Venus's thick atmosphere gradually reversed its rotation over billions of years. The math works for both explanations, but we don't have enough evidence to pick one. Venus is a reminder that planetary spin isn't always predictable. Collisions, tides, and gravitational interactions can change it, sometimes in ways that seem bizarre. Uranus is even stranger. Its rotation axis is tilted 98 degrees. The planet is essentially rolling through space on its side, with its poles pointing roughly toward and away from the Sun during different parts of its orbit. That's almost certainly the result of a giant impact early in the planet's history. Something massive hit Uranus hard enough to knock it sideways. The impact also gave Uranus a rotation period of about 17 hours, faster than Earth despite being much larger. Angular momentum from the collision was dumped into the planet's spin. Uranus has been spinning sideways ever since. Now let's talk about why Earth doesn't fall into the Sun. This seems like an obvious question, but the answer ties directly into angular momentum. Earth is orbiting the Sun at about 67,000 miles per hour. That's not rotational speed. That's orbital speed. The speed at which Earth is moving sideways relative to the Sun. If you could somehow stop Earth in its orbit, if you could remove all that sideways velocity, Earth would fall straight toward the Sun. Gravity would pull it inward, and within about 64 days, Earth would crash into the Sun's surface. But Earth isn't falling straight inward because it has that sideways velocity. Every second, gravity pulls Earth toward the Sun. Every second, Earth's sideways motion carries it to the side. The two motions combine into a curved path. That curved path is an orbit. Earth is constantly falling toward the Sun. It's just moving sideways fast enough that it keeps missing. That's what an orbit is. A continuous fall that never ends because the ground keeps curving away beneath you. The amount of sideways velocity Earth needs to maintain its orbit depends on its distance from the Sun and the Sun's mass. Closer objects need to move faster. Mercury orbits at about 105,000 miles per hour. Mars orbits at about 54,000 miles per hour. The formula comes from balancing gravitational force with centrifugal force, the outward push caused by moving in a circle. When those forces balance, the orbit is stable. The object doesn't spiral inward, it doesn't fly away, it just keeps circling. And all of that motion, the orbital velocity and the distance from the Sun, is determined by angular momentum. When Earth formed, it inherited angular momentum from the protoplanetary disk. That angular momentum fixed Earth's orbit. The planet settled into the orbital path where its angular momentum matched the gravitational pull from the Sun. Change the angular momentum and you change the orbit. Give Earth more angular momentum and it would drift outward to a higher orbit. Take away angular momentum and it would spiral inward. But as long as nothing external pushes on Earth, the angular momentum stays constant. The orbit stays stable for billions of years. Binary star systems make this even more complicated. About half of all stars in the galaxy are in binary systems, two stars orbiting a shared center of mass. In those systems, each star has its own rotation, and the pair has orbital angular momentum as well. The two types of spin interact through tides and gravitational torques. If the stars are close enough, tidal forces from one star can slow the other's rotation and vice versa. Over time, the spins synchronize. Both stars become tidally locked to the orbit, rotating once per orbit so that the same hemisphere of each star always faces its companion. That's common in tight binaries where the stars are only a few stellar radii apart. In wider binaries, the stars are far enough apart that tidal forces are weak. The spins and the orbit evolve independently. But even in those systems, angular momentum is being exchanged. If one star loses mass, say through a stellar wind, that mass carries angular momentum away with it. The binary's orbit adjusts. The system stays balanced because total angular momentum is conserved. Some binary systems are even more extreme. In a contact binary, the two stars are so close that their outer layers touch. Material flows between them. The stars share a common envelope of gas. The system looks like a peanut-shaped blob with two bright cores inside. The rotation and orbital motion are so tightly coupled that it's hard to tell where one star ends and the other begins. Angular momentum sloshes back and forth between the stars and the envelope. The entire system rotates as a single unit. These systems are rare, but they're proof that angular momentum conservation can produce structures that seem impossible. Two stars merging but not quite collapsing into one, orbiting each other while sharing the same atmosphere. The universe doesn't care if the result looks strange. It only cares that the math adds up. There's one more wrinkle. Planets don't orbit in perfect circles. Most orbits are elliptical, stretched into ovals. Earth's orbit is nearly circular, but it's not exact. The distance from Earth to the Sun varies by about 5 million kilometers over the course of a year. Earth is closest to the Sun in early January and farthest in early July. When Earth is closer, it moves faster. When it's farther, it moves slower. That variation is also a consequence of angular momentum conservation. As Earth moves closer to the Sun, the moment of inertia decreases slightly. Angular velocity increases. Earth speeds up. As Earth moves farther from the Sun, the moment of inertia increases. Angular velocity decreases. Earth slows down. The orbit isn't a circle, it's an ellipse. But the angular momentum stays constant throughout. Every planet, every comet, every asteroid obeys the same rule. Closer means faster, farther means slower. The variation is small for planets like Earth, but for comets with highly elliptical orbits, the difference is dramatic. A comet near the Sun can be moving 10 times faster than the same comet at the far end of its orbit. This is the dance of giants. Stars born, spinning from collapsing clouds, planets inheriting that spin, sculpted by collisions and tides. Orbits locked in place by angular momentum, stable for billions of years. Binary stars circling each other, exchanging spin like partners in a waltz. Moons tidally locked to planets. Planets slowly becoming tidally locked to their moons. And through it all, the same rule enforced at every scale. Angular momentum cannot be created or destroyed. It can only be redistributed. Every rotation, every orbit, every tidal bulge, every magnetic field threading through a protoplanetary disk, all of it governed by conservation. The universe built this dance without a plan. Gravity provided the choreography, angular momentum set the tempo, and the result is a cosmos where every massive object is in motion, spinning, orbiting, interacting, transferring momentum across millions of kilometers and billions of years. Nothing sits still. Nothing is allowed to. From the fastest spinning neutron stars rotating hundreds of times per second to planets like Venus rotating once every 243 days, the motion is everywhere, it's permanent, and it's all connected. A star's spin affects the disk around it. The disk's rotation determines where planets form. The planet's spins are shaped by collisions and tides. The tides transfer momentum between spin and orbit. The orbits remain stable because angular momentum is conserved. Every piece of the system is locked into the same grand structure, a cosmic machine where motion begets motion, and stillness is forbidden. And this is just stars and planets. This is the local scale, the systems we can see in detail. Wait until you step back and look at what happens when you take 100 billion stars and let them spin together. That's where the real show begins. Because if a single collapsing cloud spins faster as it shrinks, what happens when an entire galaxy does the same thing? The answer is written in every spiral arm, every rotating disk, every galactic core spinning fast enough to warp the space around it. The dance of giants doesn't end with planets, it scales up, and the next stop is the Milky Way. We've talked about clouds collapsing into stars, stars gathering planets, planets spinning because conservation left them no choice. That's the scale where human imagination still has a foothold. You can picture a planet, you can imagine a solar system, but now we need to step back, way back. Because the same rule that governs a collapsing gas cloud also governs something vastly larger. A structure containing hundreds of billions of stars, trillions of planets, vast clouds of gas and dust stretching across thousands of light years, all of it spinning together as a single coordinated system. We need to talk about galaxies, and the moment you zoom out to that scale, the universe stops looking like anything you can relate to and starts looking like something out of a fever dream. The Milky Way, the galaxy we live in, is a disk, a flat rotating plane of stars about 100,000 light-years across and only a few thousand light-years thick. From the side, it looks like two fried eggs stuck back to back. From above, it looks like a spiral. 4 or 5 major arms curving outward from a bright central bulge. The entire structure is rotating, not like a solid wheel, more like a hurricane. The inner regions spin faster than the outer regions. Stars closer to the centre complete an orbit in a few tens of millions of years. Stars near the edge, including our Sun, take about 220 to 250 million years to go around once. That's called a galactic year. The Sun has orbited the centre of the Milky Way roughly 20 times since it formed. Earth has existed for about 18 galactic years. Dinosaurs went extinct less than 1 galactic year ago. The timescales are so large that they stop meaning anything to a human brain. But the motion is real. Right now, at this exact moment, the Sun is hauling the entire solar system through space at roughly 200 to 220 kilometers per second. That's about 490,000 miles per hour. You, sitting in your chair, are moving that fast relative to the center of the galaxy. You don't feel it because everything around you, the floor, the air, the planet, the solar system, is moving together. But the motion is there. The galaxy is spinning. You're spinning with it, and you have been your entire life. Galaxies are not rare. The observable universe contains somewhere between 200 billion and 2 trillion of them. Most are smaller than the Milky Way. Some are larger. A handful are vastly larger. The biggest galaxies we've found contain over 100 trillion stars. That's a number so large it doesn't fit in human intuition. 100 trillion. Write it out and the zeros fill a line. And all of those stars, every single one, is orbiting the galactic center. The galaxy is not a static collection of stars sitting in space. It's a dynamic system held together by gravity and shaped by rotation. And every galaxy, from the smallest dwarf galaxy containing only a few billion stars to the largest giants, sprawling across millions of light years, is spinning. Some slowly, some rapidly. But all of them are in motion, because the gas clouds they formed from are spinning. And conservation of angular momentum does not make exceptions. Let's go back to the beginning. Galaxies formed in the early universe starting a few 100 million years after the Big Bang. The process was similar to star formation, just scaled up by a factor of billions. In the cosmic dark ages, vast clouds of hydrogen and helium were drifting through space. These clouds were much larger than the clouds that form stars. Some of them contained millions or billions of solar masses of gas. And like star-forming clouds, they had a tiny bit of rotation. Not much, just a faint drift, maybe one rotation every few 100 million years. Then gravity took over. Dense regions in the cloud pulled on surrounding gas. The gas fell inward. The cloud began to collapse. And as it collapsed, the moment of inertia decreased. The spin accelerated. Over millions of years, the cloud shrank and flattened. By the time the first stars ignited inside it, the cloud had become a rotating disk. That disk was the proto-galaxy. And the stars that formed inside it inherited the disk as rotation. They settled into orbits around the centre of mass. The galaxy was born spinning, and it never stopped. Most of the galaxies we see today fall into 3 broad categories: spiral galaxies, elliptical galaxies, and irregular galaxies. Spiral galaxies are the most photogenic. They're the ones you see in posters and textbooks. Flat disks with bright spiral arms winding outward from a central bulge. The Milky Way is a spiral galaxy. So is Andromeda, our nearest large neighbour. Spirals are common in the modern universe, making up maybe 60% of the galaxies we observe. They're also the galaxies where rotation is most obvious. The disk shape is a direct consequence of angular momentum conservation. Gas and stars orbiting the centre couldn't collapse any further because they were spinning too fast, so they settled into a plane, orbiting in coordinated circles. The disk is the stable configuration when you have a lot of mass rotating around a central point. Elliptical galaxies are different. They're not flat, they're 3-dimensional blobs, roughly spherical or football-shaped, with no clear disk and no spiral arms. Ellipticals tend to be older than spirals, and they rotate, but the rotation is messy. Stars in an elliptical galaxy are moving in all different directions. Some orbit in one plane, some orbit in another. There's no coordinated spin like you see in a spiral. The overall structure is held together by gravity, but the angular momentum is distributed chaotically. Most of the time, elliptical galaxies form through mergers. When two spiral galaxies collide, their disks get torn apart by tidal forces. Stars get flung into new orbits. The gas clouds smash together, igniting massive bursts of star formation. After a few 100 million years, the two galaxies merge into a single larger galaxy. And because the original disks were destroyed, the new galaxy is a blob, an elliptical. The rotation that was once organized into a clean disk is now scrambled. The galaxy still has angular momentum. The stars are still moving, but the motion is no longer organized. It's turbulent. The galaxy looks static in a photograph, but it's not. Every star is orbiting the center. It's just that no two stars are orbiting in quite the same plane. Irregular galaxies are the misfits. They're small, messy, and don't fit neatly into the other two categories. They have no clear structure, no spiral arms, no smooth elliptical shape, just a chaotic clump of stars and gas. Most irregular galaxies are the result of gravitational interactions. A small galaxy getting torn apart by a larger neighbour. A collision that didn't quite produce a clean merger. Irregular galaxies still rotate, but like ellipticals, the rotation is disorganized. There's no disk. There's no symmetry. Just stars drifting in whatever orbits the chaos left them in. The spiral galaxies are where things get interesting, because spirals don't rotate like solid objects. They rotate differentially. The inner regions spin faster than the outer regions. Picture a vinyl record spinning on a turntable. Every point on the record completes one rotation in the same amount of time. The edge of the record is moving faster than the center in terms of linear speed, but the rotation period is the same. Galaxies don't work that way. In a spiral galaxy, stars closer to the center orbit faster. Stars farther out orbit slower. The rotation period increases with distance from the center. This is called differential rotation, and it's a direct consequence of how gravity works. Stars closer to the galactic center feel a stronger gravitational pull from the combined mass of the stars and gas inside their orbit. That stronger pull makes them orbit faster. Stars farther out feel a weaker pull because the mass is more spread out. They orbit slower. The result is that the galaxy doesn't spin as a single rigid object. Different parts spin at different rates. The disk is constantly shearing. And that shearing is what creates the spiral arms. For a long time, astronomers thought spiral arms were permanent structures, regions of the galaxy where stars were more densely packed. That turned out to be wrong. If spiral arms were permanent, differential rotation would wind them up. Imagine drawing a straight line from the center of a disk to the edge, then rotating the inner part faster than the outer part. The line would curve, keep rotating, and the line would wrap around the center, forming a tighter and tighter spiral. After a few rotations, the spiral would be wound so tightly that it would blur into a solid ring. Galaxies have been rotating for billions of years. The Milky Way has completed dozens of full rotations since it formed. If spiral arms were permanent structures made of fixed groups of stars, they should be wound up into a tight coil by now, but they're not. The spiral arms of the Milky Way are still relatively loose and open. That's a problem astronomers spent decades trying to solve. The answer turned out to be both elegant and strange. Spiral arms are not permanent. They're waves. The idea is called density wave theory, and it was developed in the 1960s by astronomers Chiao Lin and Frank Hsu. The theory says that spiral arms are not made of the same stars all the time. Instead, they're regions where stars temporarily bunch up as they pass through. Think of a traffic jam on a highway. Cars enter the jam from behind, slow down, then exit from the front and speed up again. The jam itself doesn't move as fast as the cars. It's a wave of density moving through traffic. Spiral arms work the same way. Stars and gas clouds orbit the galactic center at their own speeds. But as they orbit, they pass through spiral arms, regions where the density is slightly higher. When a star enters a spiral arm, it slows down slightly because of the extra gravitational pull from the surrounding material. It spends some time in the arm, then exits and speeds up again. The arm itself rotates at a different speed than the stars. It's a pattern moving through the disk, not a fixed structure. The stars flow through the arms like water flowing through the crest of a wave. The wave stays in place, more or less, while the material passes through. The density wave triggers star formation. As gas clouds enter a spiral arm, they get compressed by the extra density. Compression can push a cloud past the threshold, where it starts collapsing under its own gravity. Stars ignite. The brightest and most massive stars are blue, and they're extremely luminous. But they're also short-lived. They only last a few million years before going supernova. So by the time a gas cloud exits the spiral arm, the massive blue stars it formed have already died. The dimmer, longer-lived red and yellow stars survive and drift out of the arm, but they're not bright enough to define the structure. The spiral arms look bright because they're full of young blue stars and glowing clouds of ionized gas. Those features trace the arms, but the arms themselves are density waves, patterns of compression moving through the disk. The stars are just passengers. This is one of the most beautiful consequences of galactic rotation. The spiral structure we see in galaxies like the Milky Way and Andromeda is not permanent. It's transient, a wave frozen in time by the fact that galaxies rotate so slowly that human lifetimes capture only a single frozen frame of their motion. The spiral arms are moving, but they move at a pace measured in tens of millions of years. From our perspective, they look static. In reality, they're flowing. Stars drift in and out. Gas clouds compress and form new stars. The massive stars die. The pattern persists because new stars are constantly being born in the arms as old stars drift out. It's a conveyor belt of star formation driven by density waves, and the whole system works because the galaxy is spinning. Differential rotation provides the shear. Density waves organize the structure. Spiral arms emerge as the visible signature of both. Now we need to talk about why galaxies rotate the way they do, because there's a problem. A big one. In the 1970s, astronomer Vera Rubin was measuring the rotation speeds of spiral galaxies. She was using spectrographs to observe how fast stars and gas clouds were moving at different distances from the galactic center. The technique is simple in principle. Light from objects moving toward us is blue shifted. Light from objects moving away is red shifted. By measuring the shift in spectral lines, you can calculate the velocity. Rubin measured the rotation speeds of stars at the edges of galaxies and compared them to the speeds closer to the center. What she found didn't make sense. The stars at the edges were moving too fast. Here's the problem. If you know how much mass is inside a star's orbit, you can calculate how fast the star should be moving. The more mass inside the orbit, the stronger the gravitational pull, the faster the star has to move to stay in orbit. If the mass is concentrated at the center, like it is in the solar system, where the Sun contains 99.8% of the total mass, then objects farther out should orbit slower. That's what Kepler's laws predict. Mercury orbits faster than Earth. Earth orbits faster than Jupiter. The farther you go, the slower the orbit. Galaxies should work the same way. Most of the visible mass in a galaxy, the stars and gas, is concentrated toward the center, so stars in the outer regions should be orbiting slower than stars near the center. And for a while, that's what happens. Rotation speed increases as you move outward from the center, but then it levels off. Stars at the edge of the galaxy are orbiting just as fast as stars halfway out. In some cases, the rotation speed stays constant all the way to the edge of the detectable disk and beyond. That's called a flat rotation curve, and it should not happen. If the only mass in the galaxy is the visible stuff, the stars and gas we can see, then the rotation curve should drop off at large distances. It doesn't. Rubin measured galaxy after galaxy and found the same thing: flat rotation curves. Stars moving faster than the visible mass could explain. There are two ways to interpret this. Either our understanding of gravity is wrong, or there's more mass in galaxies than we can see. Most of the astronomical community settled on the second explanation: dark matter. An invisible form of matter that doesn't emit light, doesn't absorb light, and doesn't interact with ordinary matter except through gravity. If galaxies are embedded in massive halos of dark matter, halos that extend far beyond the visible disk, then the rotation curves make sense. The dark matter halo provides the extra gravitational pull needed to keep the outer stars moving as fast as they are. The visible disk is just the tip of the iceberg. The real mass of the galaxy, the bulk of it, is invisible. Current estimates suggest that about 85% of the matter in the universe is dark matter. Only 15% is the ordinary stuff we can see. Stars, gas, planets, people, all of it is a minority component. The universe is mostly dark. Dark matter halos are crucial for understanding galactic rotation. When a galaxy forms, it forms inside a dark matter halo. The halo collapses first, pulled together by its own gravity. Ordinary matter, hydrogen and helium gas, falls into the halo and settles into a rotating disk. The disk is where stars form, but the halo is still there, surrounding the disk like an invisible scaffolding. The halo is roughly spherical, much larger than the disk, and it contains most of the galaxy's mass. That mass provides the gravitational pull that holds the galaxy together and keeps the outer stars orbiting fast. Without the halo, the galaxy would fly apart. The stars at the edge are moving so fast that the gravity from the visible matter alone couldn't hold them. They'd escape into intergalactic space, but they don't escape because the dark matter halo is holding them in place. The halo's gravity is what keeps the rotation curve flat. There's a minority view that disputes this. A few researchers argue that galaxies don't need dark matter at all. They claim galaxies are more like vortices in a fluid, with rotation governed by dynamics similar to water draining out of a bathtub. In that model, the rotation curve stays flat not because of unseen mass, but because the galaxy is a self-sustaining vortex in space-time, or some underlying medium. One article pushing this view argues that galaxies spin like bathtub vortices, and that the mainstream dark matter model is wrong. That's a bold claim. It's also not widely accepted. The majority of astronomers and cosmologists consider dark matter the best explanation for the rotation curves, and a host of other observations, including gravitational lensing, the cosmic microwave background, and the large-scale structure of the universe. The vortex model explains some things, but it struggles with others, and so far it hasn't displaced the dark matter paradigm. That doesn't mean it's wrong. Science is full of examples where the minority view turned out to be right, but for now the weight of evidence supports dark matter. Galaxies rotate the way they do because they're embedded in massive invisible halos that outweigh the visible matter by a factor of 5 or 6 to 1. Galaxies don't exist in isolation, they cluster. Small groups of a few dozen galaxies, larger clusters containing hundreds or thousands, superclusters containing tens of thousands, and all of those structures are interconnected by filaments of dark matter and gas stretching across hundreds of millions of light years. Galaxies move through this cosmic web, and when they get close to each other, their gravity starts to interact. Galactic interactions are common, and they can dramatically affect rotation. When two galaxies pass near each other, tidal forces stretch and distort them. Stars get pulled out of their normal orbits. Gas clouds get compressed. In some cases, the interaction triggers a burst of star formation, as compressed gas collapses into new stars. In other cases, the galaxies merge. The smaller galaxy gets torn apart and absorbed by the larger one. Over hundreds of millions of years, the two become one. The Milky Way is currently in the process of absorbing several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being pulled apart by the Milky Way's gravity. Streams of stars from the dwarf galaxy are scattered across the Milky Way's halo. The Large and Small Magellanic Clouds, two small irregular galaxies visible from the southern hemisphere, are also being pulled toward the Milky Way. In a few billion years, they'll likely merge with us. Our galaxy is eating its neighbours, slowly, but inevitably. When two large spiral galaxies collide, the result is spectacular. The disks pass through each other, but the stars almost never collide directly. Space is so empty that even in a galactic collision, the stars are too far apart to hit each other. But the gas clouds do collide, and when giant clouds of gas smash together at hundreds of kilometers per second, they compress, heat up, and ignite. The collision triggers the largest bursts of star formation anywhere in the universe. Billions of new stars form in a span of just a few million years. The galaxies light up, glowing with the combined light of countless young, massive stars. Astronomers call these starburst galaxies. They're among the brightest objects in the universe. The collision also distorts the galaxy's shapes. Tidal forces pull long streamers of stars and gas away from the main bodies. These are called tidal tails, and they can stretch for hundreds of thousands of light years. The galaxies look like they're being pulled apart, and they are. After a few 100 million years, the two galaxies merge. The disks are destroyed. The stars settle into a new, larger galaxy. Usually an elliptical. The The rotation that was once organised into two clean spirals is now scrambled. The new galaxy has angular momentum, but it's chaotic. The merger resets the structure. The spiral arms are gone. The elliptical blob is what's left. The Milky Way and Andromeda are on a collision course. Right now, Andromeda is about 2.5 million light-years away and moving toward us at roughly 110 kilometers per second. In about 4 billion years, the two galaxies will collide. The first pass will distort both galaxies. Tidal tails will form, gas clouds will collide and ignite. The night sky, if anyone is still around to see it, will be full of bright new stars. Then the galaxies will pull apart, swing around each other and collide again. After several passes, they'll merge into a single, large elliptical galaxy. Some astronomers have nicknamed the future merged galaxy Milkomeda. The Sun will probably survive. Direct collisions between stars are unlikely, but the solar system's orbit will change. We might get flung into the outer halo, we might drift closer to the galactic centre, or we might get ejected entirely, tossed into intergalactic space. By that time, the Sun will be nearing the end of its life anyway. Earth will be uninhabitable. The collision won't destroy the solar system, but it will reshuffle it. And the Milky Way's rotation, the organised spin that's been in place for over 10 billion years, will be erased, replaced by the chaotic motion of an elliptical galaxy. Rotation at the galactic scale is fundamentally the same process as rotation at the stellar scale. It's angular momentum conservation. A collapsing cloud spins faster as it shrinks. A galaxy is just a much, much larger version of the same thing. The protogalactic cloud that eventually became the Milky Way was rotating slowly. Over hundreds of millions of years, it collapsed. The rotation sped up. The cloud flattened into a disk. Stars formed in the disk and inherited its rotation. The galaxy settled into a stable configuration, where gravity pulls inward and centrifugal force from rotation pushes outward. The two forces balanced. The disk stopped collapsing. The galaxy reached equilibrium, and it's been spinning ever since. Every star, every gas cloud, every planet orbiting every star, all of it locked into the grand rotation of the galaxy. The Milky Way isn't a static photograph. It's a dynamic system in constant motion. Stars orbit. Gas flows. The spiral arms shift slowly over millions of years. Dark matter holds the whole structure together. An angular momentum, the invisible hand that's been shaping the universe since the first clouds collapsed in the cosmic dark ages, keeps everything spinning. One more point before we move on. Galaxies are loud, not in the sense of sound. Space doesn't carry sound waves, but galaxies are full of energy. Stars explode, black holes at galactic centers tear apart stars and swallow gas, releasing enormous amounts of radiation. Gas clouds collide and shock. If you had a detector sensitive to the right wavelengths, you'd see a galaxy blazing with activity, and at the center of almost every large galaxy, there's a supermassive black hole. The Milky Way's central black hole, Sagittarius A star, weighs about 4 million times the mass of the Sun. Andromeda's black hole is heavier, maybe 100 million solar masses. These black holes are not passive. They pull in gas from the surrounding disk. As the gas spirals inward, it heats up and radiates. In some galaxies, the central black hole is feeding so actively that it outshines the entire rest of the galaxy. Those are the quasars, the brightest objects in the universe. And the gas spiraling into those black holes is rotating, faster and faster as it gets closer. Angular momentum conservation applies even at the edge of a black hole. The infalling gas can't just drop straight in. It has to shed angular momentum first. It forms an accretion disk, a swirling plane of superheated matter orbiting the black hole at a significant fraction of the speed of light. The disk glows so brightly that we can see it from billions of light years away. And the rotation, the spin of that disk, is the same fundamental process we've been talking about this entire time. Shrink the size, spin faster. A collapsing cloud, a forming star, a protoplanetary disk, a galaxy, an accretion disk around a black hole, all of them governed by the same rule, all of them spinning because the universe does not allow angular momentum to vanish, it only allows it to be transformed. So galaxies are not vortices in the sense of water swirling down a drain. That's a popular image, and it's tempting because it looks right. Spiral galaxies do look like they're swirling. But the physics is different. Water draining from a bathtub is driven by pressure and fluid dynamics. The water is being pulled by gravity, yes, but it's also being pushed by the water around it. The swirl is a consequence of turbulence and the shape of the drain. Galaxies don't work that way. There's no drain. There's no fluid pushing stars around. The stars are moving in orbits governed by gravity and inertia. The spiral pattern is a density wave, not a flow of matter. The galaxy isn't collapsing into the center, it's in equilibrium. The inward pull of gravity is balanced by the outward push of rotation. The stars aren't falling, they're orbiting, and they'll keep orbiting for billions of years unless something disrupts them. A collision, a merger, a close pass by another galaxy. But left alone, the galaxy is stable, rotating, held together by dark matter and organized by the same conservation law that governs every rotating system in the universe. This is the scale where the invisible hand of angular momentum becomes almost incomprehensibly powerful. A single star rotates. 100 billion stars rotating together create a structure so large that light takes 100,000 years to cross it, and the whole thing spins, not quickly, not in any way a human could perceive, but relentlessly. The Milky Way has completed only a few dozen full rotations since it formed, but those rotations have been enough to organize the disk, generate spiral arms, trigger star formation, and build the structure we see today. Every star you can see in the night sky is part of that rotation. Every constellation, every nebula, every distant galaxy visible in a telescope, all of it is moving, spinning, orbiting, held in place by gravity and driven by momentum that's been conserved since the early universe. Galaxies are not still, they've never been still, and as long as angular momentum is conserved, they never will be. The next step is even stranger, because there's a class of objects where rotation becomes so extreme that it stops being a feature and starts being the defining characteristic. Objects spinning so fast that they warp the space around them, where the rotation isn't just motion through space, but motion of space itself. Objects where angular momentum is pushed to its absolute limit. And when you reach that limit, when you spin something as fast as the universe allows, the object stops behaving like anything we've talked about so far. It becomes something else entirely, a place where the rules bend, where time slows, where space twists. We're talking about black holes. And if you think galaxies spin fast, wait until you see what happens when all that mass collapses into a point and starts rotating at a significant fraction of the speed of light. We've seen rotation at every scale. Clouds collapsing into stars, planets spinning because conservation left them no choice, entire galaxies wheeling through space like cosmic hurricanes. At each step, the rule stayed the same. Shrink the size, spin faster. Angular momentum cannot be destroyed, it can only concentrate. And we've followed that rule from gas clouds light years across, down to planets a few thousand kilometers wide. But we're not done, because there's one more step, one final collapse. And when you take that step, when you compress mass down to the absolute limit of what physics allows, rotation stops being just motion and becomes something far stranger. It becomes a force that twists reality itself. Black holes. The name sounds dramatic, and for once the drama is earned. A black hole is what's left when a massive star runs out of fuel and collapses under its own gravity. Not a gentle collapse, a catastrophic one. The core of the star, no longer supported by the outward pressure from nuclear fusion, caves in. In less than a second, a core the size of Earth compresses to a sphere the size of a city, then smaller. The density becomes so extreme that protons and electrons are crushed together into neutrons. The collapse doesn't stop. If the core is massive enough, even neutron pressure can't hold it up. The core keeps shrinking, past the point where atoms can exist, past the point where neutrons can exist, past the point where space and time behave the way they're supposed to. The core collapses to a singularity, a point of infinite density where the laws of physics as we understand them break down completely. And around that singularity, at a specific distance determined by the mass of the collapsed core, space itself warps so severely that nothing, not even light, can escape. That boundary is the event horizon. Cross it and you're gone. Not just gone from view, gone from the universe. You've fallen into a region where escape is not difficult or unlikely. It's impossible. The future inside the event horizon does not include any path that leads back out. You can't fight your way out. You can't wait it out. You can't trick your way out. The mathematics of general relativity are unambiguous. Once you're inside, the only direction you can move is inward, toward the singularity, and you will reach it. Not because something is pulling you there, but because every possible future timeline inside the horizon ends at the singularity. It's not a destination. It's the only remaining piece of your future. That's a non-rotating black hole, a Schwarzschild black hole, named after Carl Schwarzschild, the physicist who found the first exact solution to Einstein's equations of general relativity in 1915. Schwarzschild black holes are simple, perfectly spherical. No hair, as physicists like to say, meaning no features other than mass. The event horizon is a perfect sphere. The singularity at the centre is a point. Nothing rotates, nothing moves. It's the idealized version, the kind you'd put in a textbook to explain the concept without complications. Except real black holes are not like that. Real black holes rotate, almost all of them, because the stars they formed from were rotating. And when a rotating star collapses, the rotation doesn't vanish. It concentrates. Angular momentum is conserved, and when you conserve angular momentum during a collapse that shrinks a star down to a region smaller than a city, the rotation speeds up to levels that should not be possible. Let's walk through what happens. Take a massive star, something 20 or 30 times the mass of the Sun. The star is rotating, not quickly by everyday standards, but it's spinning, maybe one rotation every few weeks. The outer layers of the star are vast, spread across millions of kilometers. The moment of inertia is enormous. The angular velocity is slow, but the angular momentum, the product of the two, is significant. Now the star runs out of fuel. Fusion stops. The core collapses. The outer layers fall inward. In less than a second, the core compresses from the size of Earth to the size of a city, then smaller. The moment of inertia drops by a factor of billions. Angular momentum stays the same, so angular velocity increases by a factor of billions. The collapsing core spins faster, much faster. If the core started with a rotation period of a few weeks, it might end up with a rotation period of a few milliseconds. The collapsed core, now a black hole, is spinning hundreds of times per second. And because the black hole is so small and so massive, that rotation warps space-time in ways that a slowly rotating star never could. This is a Kerr black hole, named after Roy Kerr, the New Zealand mathematician who found the solution to Einstein's equations for a rotating black hole in 1963. Kerr black holes are not spherical. The event horizon is flattened slightly at the poles, bulging at the equator like a squashed ball. The faster the black hole spins, the more pronounced the distortion. And outside the event horizon, there's a second boundary, a region called the ergosphere. The ergosphere is one of the strangest features in all of physics. Inside the ergosphere, space-time itself is being dragged around the black hole. This effect is called frame dragging, and it's a prediction of general relativity that has been confirmed in weaker forms around rotating planets and stars. But around a black hole, the effect is extreme. Inside the ergosphere, space-time is rotating so fast that nothing can stay still. Not matter, not light, not anything. If you were hovering just outside the event horizon of a Kerr black hole, you would be dragged around the black hole whether you liked it or not. You could fire your rockets at full thrust in the opposite direction, trying to stay in place, and you would still get pulled along. Because it's not that something is pushing you, it's that the space-time you're sitting in is rotating. And you, being made of matter that exists in space-time, have no choice but to rotate with it. The ergosphere extends from just outside the event horizon, out to a distance that depends on the black hole's spin. For a maximally rotating black hole, a black hole spinning as fast as physics allows, the ergosphere can extend outward by a factor of 2 compared to the event horizon radius. That's a huge region, and inside that region the fabric of space is twisted into a vortex. If you dropped an object into the ergosphere, it would start orbiting the black hole even if you dropped it straight down with no sideways velocity. The rotation of space-time itself would curve its path. The object would spiral inward, dragged by the spinning geometry of the universe. This is not a metaphor. Space-time is a physical thing in general relativity. It's the stage on which matter and energy move. And that stage can be bent, stretched, compressed, and in the case of a rotating black hole, twisted like a towel being wrung out. Frame dragging happens around any rotating massive object, but the effect is tiny unless the object is incredibly dense. Earth drags space-time along with it as it rotates, but the effect is so small that it took decades of precise satellite measurements to detect it. In 2004, NASA's Gravity Probe B mission confirmed that Earth's rotation does drag space-time, but the twist is minuscule. A gyroscope in orbit around Earth will precess, slowly changing its orientation by only a few milliseconds per year because of frame dragging. That's about the width of a human hair seen from 10 kilometers away, barely detectable even with the most sensitive instruments we have. Around a rotating black hole, the effect is not subtle. Frame dragging near the event horizon of a Kerr black hole is so strong that space-time is rotating at a significant fraction of the speed of light. Matter caught in that rotating space-time has no hope of resisting. It gets swept along, and as it spirals inward, it speeds up. Because the closer you get to the black hole, the faster space-time is rotating. By the time matter crosses the event horizon, it's moving at velocities approaching the speed of light. Not because something accelerated it, because the space-time it's embedded in is moving that fast. Now let's add one more element: gas. Black holes don't sit in empty space. Most of them are surrounded by material. Gas from a companion star if the black hole is in a binary system, gas from the interstellar medium if the black hole is drifting through a cloud, or gas from the disruption of a star that wandered too close. That gas doesn't fall straight into the black hole. It has angular momentum. It's moving sideways relative to the black hole, and because angular momentum is conserved, the gas can't just drop in. It has to spiral. It forms an accretion disk, a flat rotating structure of gas orbiting the black hole. The gas in the disk is moving at a significant fraction of the speed of light. The inner edge of the disk, the region closest to the event horizon, is moving the fastest. And because the gas is moving so fast, friction between adjacent layers of gas heats the material to extreme temperatures, millions of degrees, hot enough that the gas emits X-rays. The disk glows brightly. In some cases, the accretion disk around a black hole is brighter than entire galaxies. The energy comes from gravity. As gas spirals inward, it loses gravitational potential energy. That energy has to go somewhere. It goes into heat. The gas heats up, radiates, and slowly loses energy, allowing it to spiral closer. The process is efficient, terrifyingly efficient. Matter falling into a black hole can convert up to 40% of its mass into radiated energy if the black hole is rotating rapidly. For comparison, nuclear fusion, the process that powers stars, converts less than 1% of mass into energy. Black hole accretion is the most efficient energy generation process we know of in the universe. The accretion disk is not a calm, orderly structure. It's turbulent. Magnetic fields thread through the gas, amplifying turbulence and generating instabilities. Blobs of hot gas spiral inward faster than the surrounding material, forming bright spots that flare and fade. The inner edge of the disk is a chaotic boundary where gas is on the verge of crossing the event horizon. Some of the gas makes it in. Some gets flung outward by magnetic forces or turbulence, escaping the black hole entirely, and in some cases twin jets of material shoot out from the poles of the black hole perpendicular to the accretion disk. These jets are powered by the black hole's rotation. The exact mechanism is still debated, but the leading theory involves magnetic fields anchored in the accretion disk and twisted by the black hole's spin. The twisting magnetic fields accelerate particles to nearly the speed of light and fling them outward in narrow beams. The jets can extend for thousands of light years, far beyond the galaxy containing the black hole. They're visible in radio wavelengths, glowing with the synchrotron radiation emitted by electrons spiraling around magnetic field lines. The jets are one of the most dramatic consequences of black hole rotation. A spinning black hole doesn't just pull things in, it also throws things out, and the energy for both comes from the same source, the rotational energy of the black hole itself. Here's where things get deeply strange. A rotating black hole contains an enormous amount of energy stored in its spin. That energy can, in principle, be extracted. Not by anything falling into the black hole. Once you're inside the event horizon, you're done. But in the ergosphere, the region outside the horizon where space-time is being dragged around, there's a loophole, a process called the Penrose process, named after physicist Roger Penrose, who described it in 1969. The idea is this: an object falls into the ergosphere. Inside the ergosphere, the object splits into two pieces. One piece falls into the black hole, the other piece escapes. If you arrange the split carefully, the piece that falls in can have negative energy relative to an outside observer. That sounds impossible, and in most regions of spacetime it is. But inside the ergosphere, where spacetime itself is rotating, negative energy states are allowed. When the negative energy piece falls into the black hole, it reduces the black hole's total energy. The black hole slows down, it loses rotational energy, and that energy has to go somewhere. It goes into the escaping piece. The escaping piece flies away with more energy than the original infalling object had. You've extracted energy from the black hole's rotation. The black hole spins slightly slower. You walk away with free energy. The universe balances the books by reducing the black hole's angular momentum. The Penrose process is theoretically possible but practically difficult. Splitting an object at exactly the right moment in exactly the right way inside the ergosphere is not something you can do with current technology or anything resembling current technology. But the principle is sound. Rotating black holes are batteries, enormous reservoirs of rotational energy that could, if you had the right tools, be tapped. Some astrophysicists have speculated that advanced civilizations might use the Penrose process to extract energy from black holes. It's one of the few mechanisms that could provide enough power to run a civilization spanning multiple star systems. You wouldn't need to burn fuel or build solar panels. You just need to drop matter into the ergosphere of a rotating black hole and catch the pieces that come flying back out with extra energy. As long as the black hole is spinning, the battery is charged, and black holes can spin for an extraordinarily long time. Billions of years, potentially trillions. A slowly spinning black hole losing energy through the Penrose process would eventually stop spinning, but the timescale is so long that it's almost irrelevant. For practical purposes, a black hole is an inexhaustible energy source. Now we come to the question of how fast a black hole can actually spin. There's a limit. It's not arbitrary. It's baked into the mathematics of general relativity. The spin of a black hole is described by a dimensionless number, usually written as the letter A in the equations. For a non-rotating black hole, A equals 0. For a maximally rotating black hole, A equals 1. That maximum is called the extremal limit. If a black hole were spinning faster than the extremal limit, the event horizon would disappear. The singularity at the center would be exposed. Naked singularities, as they're called, are theoretically possible in the math, but are widely believed to be forbidden by something called the cosmic censorship conjecture. The idea is that the universe doesn't allow singularities to be visible. Every singularity has to be hidden behind an event horizon. If you try to spin a black hole past the extremal limit, something stops you. Maybe infalling matter adds angular momentum and mass in just the right ratio to keep the spin below the limit. Maybe the black hole radiates away excess spin through gravitational waves. The exact mechanism isn't clear, but observations suggest that real black holes do not exceed the extremal limit. Most black holes we've measured are spinning at somewhere between 50 and 98% of the maximum. Close to the limit, but not quite at it. Measuring the spin of a black hole is not straightforward. You can't see the black hole directly. You can't watch it rotate. What you can do is observe the accretion disk, the innermost stable orbit around a black hole. The closest distance where matter can orbit without immediately falling in depends on the black hole's spin. For a non-rotating black hole, the innermost stable orbit is at 3 times the radius of the event horizon. For a maximally rotating black hole, the innermost stable orbit can be as close as half the event horizon radius, and that's measured from the black hole's equator where the spin is fastest. The difference is significant. Gas in the accretion disk orbiting closer to the event horizon is moving faster and heating up more. The spectrum of X-rays emitted by the disk changes depending on how close the gas can get. By analysing the X-ray spectrum, astronomers can infer the radius of the innermost stable orbit, and from that calculate the black hole's spin. It's an indirect measurement, but it works, and the results show that many black holes are spinning very fast. Some are spinning at more than 98% of the maximum allowed speed. These are not gentle rotations. These are objects where the surface, if black holes had surfaces, would be moving at 98% of the speed of light. The equator of a maximally spinning black hole is a blur of space-time moving so fast that time itself slows down relative to a distant observer. Time dilation near a black hole is extreme. If you were hovering just outside the event horizon of a non-rotating black hole, time for you would pass much more slowly than time for someone far away. This is gravitational time dilation, a prediction of general relativity that's been confirmed in weaker forms here on Earth. Clocks at higher altitudes, where gravity is weaker, tick slightly faster than clocks at sea level. The effect is tiny, but GPS satellites have to account for it, or their positioning data would drift out of sync within hours. Near a black hole, the effect is not tiny. An hour for you hovering near the event horizon might correspond to years or decades for someone far away. And if the black hole is rotating, the time dilation gets even worse in certain regions because frame dragging is pulling space-time along faster than a non-rotating black hole would. Time near a spinning black hole doesn't just slow down, it twists. The distinction between space and time starts to blur. Inside the ergosphere, one of your spatial dimensions gets mixed with time in a way that's hard to visualize. You can't stay still, not because you lack the engine power, but because staying still would require moving backward in time. The geometry of space-time has been twisted so severely that the concepts of space and time as separate things stop making sense. This is what rotation does when you push it to the absolute limit. It stops being motion and starts being geometry. A spinning black hole is not an object rotating through space. It's a region where the rotation has been woven into the structure of space-time itself. The black hole is the spin. The two are inseparable, and the consequences ripple outward. Matter spiraling into the black hole gets swept up in the twisted space-time. Magnetic fields threading through the accretion disk get wound tighter and tighter by the rotation until they snap and reconnect, releasing bursts of energy. Jets of particles get flung out along the rotation axis at nearly the speed of light. Gravitational waves, ripples in space-time caused by the motion of massive objects, radiate outward from the black hole, carrying away energy and angular momentum. Every process happening near a spinning black hole is shaped by the fact that space-time itself is rotating. The black hole is a vortex, not in space, in space-time, and everything nearby is caught in the flow. The energy output from a spinning black hole can be staggering. Quasars, the brightest objects in the universe, are powered by supermassive black holes at the centers of galaxies. These black holes weigh millions or billions of times the mass of the Sun, and they're surrounded by accretion disks feeding them with gas at rates of several solar masses per year. The disks are hot, bright, and incredibly energetic. A single quasar can outshine an entire galaxy of hundreds of billions of stars. The energy comes from the gravitational potential energy of the infalling gas, and if the black hole is spinning, from the rotational energy of the black hole itself. Some quasars are so bright that we can see them from billions of light years away. We're seeing them as they existed when the universe was less than 1 billion years old. The light has been travelling toward us for over 90% of the age of the universe, and in that light, we can see the signature of black hole spin, the broadening of spectral lines caused by gas moving at relativistic speeds, the polarization of light bent by the twisting space-time near the event horizon, the X-ray emissions from gas spiraling inward at the innermost stable orbit. All of it points to black holes spinning at close to the maximum rate allowed by physics. Stellar mass black holes, the kind formed from the collapse of individual stars, are smaller, but no less extreme. A 10 solar mass black hole has an event horizon radius of about 30 kilometers. If that black hole is spinning at 90% of the maximum, the equator of the event horizon is moving at 90% of the speed of light. That's 270,000 kilometers per second. The surface of the black hole, if we could see it, would be a featureless blur, but we can't see it. The event horizon is black because no light escapes. What we can see is the accretion disk, and in X-ray binary systems where a black hole is pulling gas off a companion star, the accretion disk is bright. The gas heats up to millions of degrees as it spirals inward. The disk emits X-rays that we can detect with space-based telescopes. By studying the X-ray spectrum and how it varies over time, astronomers can measure the black hole's mass and spin. Some stellar mass black holes are spinning at over 95% of the maximum. They're rotating so fast that the innermost stable orbit is almost touching the event horizon. Gas in that orbit is moving at close to the speed of light. It completes one orbit in a few milliseconds. The environment is so extreme that general relativity is the only theory that can describe it. Newtonian gravity breaks down completely. Time and space are so warped that the usual rules stop applying. Gravitational waves from merging black holes have given us a new way to study black hole spin. When two black holes spiral into each other and merge, they emit gravitational waves, ripples in space-time that propagate outward at the speed of light. The shape of the gravitational wave signal depends on the masses and spins of the merging black holes. By analysing the signal, scientists can extract both quantities. LIGO, the Laser Interferometer, Gravitational Wave Observatory, has detected dozens of black hole mergers since 2015. The data shows that many of the merging black holes were spinning. Some were spinning rapidly, some were spinning slowly. The spins were often misaligned, meaning the two black holes were rotating in different directions relative to their orbital plane. That tells us something about how the black holes formed. If they formed together as a binary system from two massive stars, their spins should be aligned. If they formed separately and later captured each other, their spins can be misaligned. The gravitational wave data is starting to fill in the picture of how black holes spin and how their spins evolve over time. When two black holes merge, the final black hole spin depends on the spins and masses of the original two. If both were spinning in the same direction as the orbit, the final black hole can end up spinning faster than either of the originals. If they were spinning in opposite directions, the spins can partially cancel out. The merger also radiates away a significant fraction of the system's total energy and angular momentum in the form of gravitational waves. By the time the final black hole settles down, it's usually spinning at somewhere between 30 and 70% of the maximum. The exact number depends on the details of the merger, but the result is always a Kerr black hole. A spinning black hole with an ergosphere, frame dragging, and all the other strange features that come with rotation. And here's the thing. Almost every black hole we've observed is spinning. Slowly spinning black holes are rare. That makes sense. Stars rotate. When they collapse, the rotation concentrates. The resulting black hole inherits the angular momentum. Even if the original star was rotating slowly, the collapse amplifies the spin. Black holes are born spinning, and they stay spinning. There's no friction in space, there's no air resistance. Once a black hole is rotating, it keeps rotating. The only way to slow it down is to add material with angular momentum in the opposite direction, or to radiate away angular momentum through gravitational waves. Both processes are slow. A black hole left alone will spin for billions of years without slowing down measurably. The rotation is as permanent as the black hole itself. Angular momentum, conserved from the collapsing star locked into the geometry of spacetime, persists until the black hole evaporates through Hawking radiation trillions of years in the future. And even then, the angular momentum doesn't vanish. It gets radiated away along with the mass and energy as the black hole slowly shrinks. Black holes are the ultimate test case for angular momentum conservation. Take a star, compress it to a point. The rotation doesn't disappear, it concentrates. The black hole spins faster and faster as it shrinks, limited only by the maximum allowed by general relativity. And that spin isn't a detail, it's not a minor feature you can ignore. The spin shapes the space-time around the black hole. It determines the size and shape of the ergosphere. It affects the accretion disk. It powers the jets. It sets the rate at which energy can be extracted from the black hole. Spin is as fundamental to a black hole's identity as its mass. A Schwarzschild black hole, the non-rotating kind, is an idealization. Real black holes are Kerr black holes, spinning, twisting space-time, dragging everything nearby into the vortex, and the energy stored in that spin is enormous. A 10 solar mass black hole rotating at the maximum rate contains about 10% of its rest mass energy in the form of rotational energy. That's more energy than the Sun will radiate over its entire 10 billion year lifetime, stored in the spin of an object the size of a city, and all of it in principle extractable. We've come a long way from collapsing gas clouds, from rotation periods of millions of years down to rotation periods of milliseconds, from objects light years across down to objects a few dozen kilometers wide. At every step the same rule applied. Angular momentum is conserved, shrink the size, spin faster, and black holes at the end of that road. The final collapse. The point where you can't shrink any further because you've compressed mass down to the limit where space-time itself breaks. But even at that limit, the rule still holds. The black hole spins, faster than anything else in the universe, and the spin, locked into the geometry of space-time, becomes part of the black hole structure. You can't separate the rotation from the object. They're the same thing, but we're still not done, because there's one more place where spin shows up, and it's stranger than anything we've talked about so far, because up until now, every example of rotation we've discussed has been classical. Objects moving through space or space-time. Things you could, in principle, watch spin. Stars, planets, galaxies, black holes, all of them rotating in the usual sense. But there's a type of spin that doesn't work that way. A spin that's built into particles at the quantum level, a spin that has nothing to do with motion through space, a spin that just is, an intrinsic property like mass or charge. And when you start looking at that spin, at the quantum twist baked into every particle in the universe, the rules change. Angular momentum is still conserved, but the meaning of rotation itself becomes something you can't visualize, something you can only describe with math. And that spin, that quantum spin, is what we're going to look at next. Because if black holes are where classical rotation reaches its limit, quantum mechanics is where rotation stops making sense and starts being something else entirely. We've been climbing a ladder, gas clouds collapsing into stars, stars spinning because conservation gave them no choice, planets inheriting that spin and holding onto it for billions of years, galaxies wheeling through space like cosmic hurricanes, black holes rotating so fast they twist space-time itself into knots. At every step the rules stay the same. Angular momentum is conserved. Objects rotate because they've always been rotating, because the spin was there from the beginning and the universe doesn't allow it to vanish. That's classical rotation, objects moving through space. Motion you can picture, even if the speeds involved are beyond anything a human can experience directly. You can imagine a planet spinning. You can picture a galaxy rotating, even if it takes 200 million years to complete one turn. The mental model works. You have an object. The object rotates. The rotation is motion. But now we need to talk about a different kind of spin. A spin that has nothing to do with motion through space. A spin that doesn't involve anything rotating in the way you think rotation works. A spin that's built into the fabric of reality at the smallest scales, woven into every particle that has ever existed. Quantum spin. And if you think black holes warping spacetime is strange, wait until you see what happens when you try to make sense of an electron spinning. Let's start with what we know. Matter is made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons sit in the nucleus at the center. Electrons orbit the nucleus in a cloud of probability, though calling it an orbit is misleading because electrons don't move in neat circles the way planets do. The electron cloud is a region where the electron is likely to be found if you measure it. But until you measure it, the electron doesn't have a definite position. It's smeared out over space, existing in a superposition of all possible locations at once. That's quantum mechanics in a nutshell. Particles don't have definite properties until you observe them. Before the observation, they exist in a state of possibility. After the observation, they collapse into a single outcome. The math works, the predictions are stunningly accurate, and the interpretation makes no sense to a human brain trained by millions of years of evolution to think in terms of objects with definite positions moving through definite paths. Quantum mechanics doesn't care. It works whether or not you can visualize it. Electrons have mass. They have charge, negative charge specifically, which is why they're attracted to the positively charged protons in the nucleus, and electrons have spin, not metaphorical spin, not some abstract property that physicists named spin because they couldn't think of a better word. Actual angular momentum, measurable angular momentum. An electron carries intrinsic angular momentum even when it's sitting still, even when it's not moving through space, even when it's not rotating in any classical sense. The angular momentum is there, always. It's a property of the electron itself, like its mass or charge. You can't turn it off, you can't remove it. An electron without spin would not be an electron, it would be something else. Spin is as fundamental to the identity of an electron as any other property it has. And the same is true for protons, neutrons, photons, quarks, and every other elementary particle in the universe. They all have spin, built-in, permanent, intrinsic. Here's where things start to break. In classical mechanics, angular momentum is the product of mass, velocity, and distance from the center of rotation. A spinning top has angular momentum because its mass is rotating around an axis. The faster it spins, the more angular momentum it has. The more mass it has, the more angular momentum. If the top stops spinning, the angular momentum goes to zero. That's how rotation works in the everyday world. But an electron is not a spinning top. For one thing, electrons are point particles as far as we can tell. They have no measurable size. If an electron has any physical extent at all, it's smaller than anything we can currently probe. Experiments have put an upper limit on the electron's radius at something like 10 to the power of negative 22 meters. That's a billion times smaller than a proton. For practical purposes, the electron is a point. It has no surface, no edge, no interior. It's a dot of charge and mass with no dimension. So if an electron is a point, what exactly is spinning? The answer is nothing. The electron is not literally rotating. The spin is not motion. It's an intrinsic property, a kind of angular momentum that exists without anything physically turning. And yes, that sounds like nonsense. It should sound like nonsense. Because the human brain evolved to understand objects that you can see and touch, objects that behave according to the rules of classical physics. Quantum mechanics is not classical physics. The rules are different. And spin is one of the first places where the difference becomes unavoidable. An electron has angular momentum. That angular momentum is real. You can measure it. It affects how the electron interacts with magnetic fields. It determines the electron's behavior in atoms. But the angular momentum is not the result of the electron rotating. It's just there. A property the electron was born with. The universe at the quantum level does not require motion to have angular momentum. Particles can have spin without spinning. And if that bothers you, if that feels wrong, you're in good company. It bothered every physicist who first encountered it too. The discovery of electron spin came in the 1920s. Physicists were trying to understand the fine structure of atomic spectra, the tiny splits in the spectral lines emitted by atoms. The splits couldn't be explained by the known properties of electrons, their charge and mass and orbital motion around the nucleus. Something was missing. In 1925, two young Dutch physicists, George Uhlenbeck and Samuel Goldschmidt, proposed that electrons have an additional property, an intrinsic angular momentum that they called spin. The idea was controversial. Wolfgang Pauli, one of the giants of quantum theory, initially dismissed it. The math seemed to require the surface of the electron to be moving faster than the speed of light if the spin were real physical rotation. That's impossible. Nothing can move faster than light. So the idea didn't make sense, but the predictions worked. When you included electron spin in the calculations, the spectral lines matched the observations. The theory explained things that couldn't be explained any other way, so physicists accepted it. Reluctantly. With the understanding that spin was not actually rotation, but some other kind of property that behaved like angular momentum without involving motion. The name stuck because it was convenient, but the name is misleading. Spin is not spinning. The most direct demonstration of quantum spin is the Stern-Gerlach experiment, first performed in 1922 by Otto Stern and Walter Gerlach. They took a beam of silver atoms and passed it through a magnetic field. The magnetic field was not uniform. It was stronger at the top than at the bottom, creating a gradient. In classical physics, if the silver atoms had magnetic moments due to some kind of internal motion, you'd expect the beam to spread out into a continuous smear. Some atoms would be deflected upward, some downward, depending on the orientation of their magnetic moment. The deflection would be smooth, a spectrum. That's not what happened. The beam split into two distinct spots, not a spread, not a blur, two sharp locations. Half the atoms were deflected up, half were deflected down, nothing in between. The experiment showed that whatever property was causing the magnetic moment, it was quantized. It came in discrete values, not a continuous range. The atoms were not randomly oriented. They were forced into one of two possible states, spin up or spin down. That's quantization. And it's one of the defining features of quantum mechanics. Properties that in the classical world can take any value are restricted to specific discrete values in the quantum world. Spin is one of those properties. Electrons have spin 1/2. That's not a speed. It's a quantum number describing the magnitude of the spin angular momentum. Spin 1/2 means that if you measure the electron's spin along any axis, you get one of two results, spin up or spin down, plus 1/2 or minus 1/2 in units of the reduced Planck constant, the fundamental unit of angular momentum in quantum mechanics. You never measure an electron with spin 0. You never measure an electron with spin 3/4. It's always 1/2 or negative 1/2. Always. The electron does not have a definite spin direction until you measure it. Before the measurement, the electron is in a superposition of spin up and spin down. It's both at once, in a sense that doesn't map onto classical intuition. When you measure it, the superposition collapses and you get one outcome. 50-50 odds if the electron was in a balanced superposition. After the measurement, the electron has a definite spin along the axis you measured. But if you measure along a different axis, the electron's spin along the first axis becomes undefined again. Measuring one component of spin disturbs the other components. You can't know the spin in all directions at once. That's Heisenberg's uncertainty principle applied to spin. The more precisely you know one component, the less you can know about the others. Protons and neutrons also have spin 1/2. Photons have spin 1. Other particles have different spins. The Higgs boson has spin 0. Gravitons, if they exist, would have spin 2. The spin of a particle is a fixed property. It doesn't change. An electron is always spin 1/2. A photon is always spin 1. The spin is part of what defines the particle, and the value of the spin has deep consequences for how particles behave. Particles with half-integer spin, like electrons, protons, and neutrons, are called fermions. Particles with integer spin, like photons, are called bosons. Fermions and bosons obey different statistical rules. Fermions obey the Pauli exclusion principle. Bosons don't. That difference is responsible for the entire structure of matter. Everything solid, everything stable, everything that doesn't collapse into an undifferentiated blob exists because fermions can't occupy the same quantum state. That's the exclusion principle, and it's a direct consequence of spin. Wolfgang Pauli formulated the exclusion principle in 1925. The principle states that no two fermions can occupy the same quantum state simultaneously. A quantum state is defined by a set of quantum numbers, properties like energy, orbital angular momentum, and spin. If two electrons are in the same atom, they can have the same energy and the same orbital angular momentum, but they have to have different spins, one spin up, one spin down. That's the only way to satisfy the exclusion principle. The principle explains why atoms don't collapse. Electrons in an atom are attracted to the nucleus by the electromagnetic force. In classical physics, you'd expect all the electrons to fall into the nucleus, spiraling inward and releasing energy until they crash into the protons. That doesn't happen. Electrons settle into discrete energy levels, shells around the nucleus, and only a limited number of electrons can fit in each shell. The first shell can hold 2 electrons, one spin up and one spin down. The second shell can hold 8. The third shell can hold 18. The pattern continues. Once a shell is full, additional electrons have to go into higher energy shells farther from the nucleus. The atom has structure, stability, chemistry. All because electrons can't share the same quantum state. All because fermions obey the exclusion principle. And the exclusion principle exists because fermions have half-integer spin. The connection between spin and statistics, the rule that determines whether particles are fermions or bosons, is called the spin statistics theorem. It's one of the most important results in quantum field theory, proven in the 1940s by Wolfgang Pauli and others. The theorem says that particles with half-integer spin must be fermions, and particles with integer spin must be bosons. There's no deep intuitive reason why this has to be true. It falls out of the mathematics of quantum field theory combined with the requirements of special relativity. The proof is technical and doesn't lend itself to simple explanations, but the consequence is clear. Spin determines whether particles can pile on top of each other or whether they're forced to stay apart. Bosons, particles with integer spin, can occupy the same state. You can have arbitrarily many photons in the same quantum state. That's how lasers work. A laser is a coherent beam of photons all in the same state, all moving in the same direction with the same frequency and phase. You couldn't do that with fermions. Fermions resist being in the same state, they spread out. They fill up available states one by one. That resistance, that spreading, is what gives matter its structure. Atoms have size because electrons can't all sit in the ground state. Solid objects resist compression because the electrons in the material are already packed into the lowest available states, and pushing them closer requires enormous energy. The hardness of matter, the fact that you can't stick your hand through a table, is a consequence of the Pauli exclusion principle. And the exclusion principle is a consequence of spin. Spin also determines how particles interact with magnetic fields. A charged particle with spin generates a magnetic moment, a tiny magnetic field of its own. The magnetic moment is proportional to the spin. An electron with spin 1/2 has a measurable magnetic moment. You can use that magnetic moment to manipulate the electron. Apply an external magnetic field, and the electron's spin will precess, wobbling around the direction of the field like a spinning top wobbling in Earth's gravitational field. The precession frequency depends on the strength of the magnetic field. Change the field and you change the precession. This is the basis for a huge range of technologies. Magnetic resonance imaging, MRI, works by manipulating the spins of hydrogen nuclei, protons, in the water molecules in your body. The protons are placed in a strong magnetic field. Their spins align with the field. Then a radio frequency pulse is applied, knocking the spins out of alignment. As the spins relax back, they emit radio waves that can be detected. The frequency and timing of those waves depend on the local environment, the type of tissue the water is in. By mapping the signals, you can build an image of the interior of the body. The entire technique relies on quantum spin, the fact that protons have intrinsic angular momentum and respond to magnetic fields in predictable ways. MRI wouldn't work if spin were just a metaphor. The spin is real. The angular momentum is real, and the interaction with magnetic fields is real. Quantum computing is another application of spin. A classical computer stores information in bits, units that are either 0 or 1. A quantum computer stores information in qubits, quantum bits that can be 0, 1, or a superposition of both. The superposition allows a quantum computer to perform certain calculations much faster than a classical computer. One way to build a qubit is to use the spin of an electron. Spin up represents 1, spin down represents 0. The electron can be in a superposition of spin up and spin down, representing both 0 and 1 simultaneously. You can manipulate the qubit by applying magnetic fields or microwave pulses that rotate the spin. You can entangle qubits, linking their states so that measuring one affects the other, and you can perform computations by carefully choreographing the evolution of the qubit's spins. Quantum computers are still in the early stages of development. They're fragile, they require extreme cooling, they're prone to errors, but they work. And they work because quantum spin is a real, controllable property of particles. You can prepare a spin state, you can rotate it, you can measure it, and the outcomes obey the laws of quantum mechanics with exquisite precision. Spin is also central to the standard model of particle physics, the theory that describes all known particles and their interactions. The standard model divides particles into fermions and bosons. The fermions are the matter particles, quarks and leptons. Quarks combine to form protons and neutrons. Leptons include electrons and neutrinos. All the fermions have spin 1/2. The bosons are the force carriers. Photons carry the electromagnetic force. Gluons carry the strong nuclear force. W and Z bosons carry the weak nuclear force. The Higgs boson gives particles mass. All the bosons except the Higgs have spin 1. The Higgs has spin 0. The spin of a particle determines how it couples to other particles, how it interacts. Spin is not a side detail. It's written into the structure of the theory. Change the spin of a particle, and you change its behavior fundamentally. It becomes a different particle. The universe at the quantum level is built out of particles defined by a handful of properties: mass, charge, spin. Take away any of those and the particle doesn't exist in the form we recognize. Spin is as fundamental as anything gets. Now we come to the truly strange part. Quantum spin is not rotation, but it obeys the same mathematical rules as classical angular momentum. It adds and subtracts the same way. It processes in magnetic fields the same way. It's conserved the same way. If you have a system of particles, the total spin of the system is the vector sum of the individual spins, and that total spin is conserved unless something external acts on the system. A particle can decay into other particles, but the total spin before the decay has to equal the total spin after. A photon can be absorbed by an atom, but the atom's angular momentum changes by exactly the amount the photon was carrying. Spin is angular momentum. It's just angular momentum that doesn't come from motion, and the universe treats it the same way it treats the angular momentum of a spinning planet or a rotating galaxy. It's all the same currency, all conserved by the same rule. There's a mathematical framework that describes spin in quantum mechanics. It's built on objects called spinors, mathematical entities that transform in a specific way when you rotate the coordinate system. Spinors are strange. If you rotate a spinor by 360 degrees, a full turn, you don't get back to where you started. You get the negative of where you started. You have to rotate it by 720 degrees, 2 full turns, to return to the original state. This is not a quirk of the math. It's a physical property of spin 1/2 particles. An electron rotated by 360 degrees picks up a minus sign in its quantum state. That minus sign has measurable consequences. It affects interference patterns in quantum experiments. It's real. And it's one of the clearest signs that quantum spin is not classical rotation. Nothing in classical physics behaves that way. A spinning top rotated by 360 degrees looks exactly the same as it did before. An electron does not. Quantum mechanics is playing by different rules, and spin is one of the places where those rules are most visible. Some researchers have proposed deep connections between quantum spin and the structure of space-time itself. One line of thinking ties spin 1/2 degrees of freedom to the geometry of four-dimensional space-time. The idea is that the reason spin exists, the reason particles have this intrinsic angular momentum, is that they're fundamentally tied to the fabric of space-time in a way that classical objects are not. Particles are not little balls bouncing around in space. They're excitations of quantum fields, and those fields are woven into space-time. Spin might be a reflection of how those fields interact with the underlying geometry of the universe. This is speculative. It's not settled science, but it's an active area of research. Some physicists argue that understanding spin at a deeper level might require unifying quantum mechanics and general relativity, finding a theory of quantum gravity that explains why particles have the spins they do and why spin is quantized in the way it is. For now, we don't have that theory. We have the Standard Model, which describes spin perfectly well as a fundamental property. But the Standard Model doesn't explain why spin exists. It just takes it as given. The electron has spin 1/2. The photon has spin 1. Those are inputs to the theory, not predictions. A deeper theory might explain where those numbers come from, or it might not. It's possible spin is just a brute fact about the universe, a property that exists because it has to, with no further explanation available. There's also a connection between spin and quantum entanglement. When two particles are entangled, their quantum states are linked. Measuring the spin of one particle instantly determines the spin of the other, even if the particles are separated by large distances. This is not because information travels faster than light. It's because the two particles share a single quantum state. They're not two independent systems. They're one system described by a joint wave function. Entanglement is one of the most counterintuitive features of quantum mechanics. Einstein famously called it spooky action at a distance, and argued that it showed quantum mechanics was incomplete. He was wrong. Quantum mechanics is complete, as far as we can tell. Entanglement is real, and spin is one of the easiest properties to entangle. You can create pairs of photons with entangled spins, measure the spin of one photon, and you instantly know the spin of the other. The correlation is perfect, stronger than anything classical physics allows. Experiments have confirmed this over and over. Entangled spins violate Bell's inequalities, a set of mathematical constraints that any local hidden variable theory would have to satisfy. Quantum mechanics violates those inequalities. Reality is not locally real in the way classical intuition suggests. Particles do not have definite properties independent of measurement. And spin, because it's easy to manipulate and measure, has been the testing ground for these ideas for decades. One of the surprising facts about spin is that even massless particles have it. Photons have spin, even though they have no rest mass. A photon's spin is related to its polarization. Light can be polarized, meaning the electric field oscillates in a specific direction. Circular polarization, where the electric field rotates as the light wave propagates, corresponds to the photon having spin. Right circular polarization is spin +1. Left circular polarization is spin -1. The spin is carried by the photon and can be transferred to other particles when the photon is absorbed. This is how light can exert torque, a twisting force, on objects. Shine circularly polarized light on a suspended particle, and the particle will start to rotate because the light is transferring angular momentum. The effect is tiny, but it's measurable. It's been used to trap and manipulate small objects in optical tweezers, a technique that uses focused laser beams to hold and move microscopic particles. The photons in the laser beam carry spin, and that spin can be used to control the rotation of the trapped particle. All of this works because photon spin is real angular momentum, conserved and transferable just like the angular momentum of a spinning wheel. Quantum spin also plays a role in exotic states of matter. Superconductors, materials that conduct electricity with zero resistance, rely on the pairing of electrons with opposite spins. The pairs, called Cooper pairs, behave as bosons, even though individual electrons are fermions. Two spin 1/2 particles can combine to make a spin 0 or spin 1 pair, which is a boson. The Cooper pairs can occupy the same quantum state, forming a coherent quantum fluid that flows without resistance. The details are complex, but the point is that spin is central to the phenomenon. change the spin pairing and the superconductivity disappears. Superfluids, materials that flow without viscosity, also involve spin. Helium-3, an isotope of helium, becomes a superfluid at extremely low temperatures. The helium-3 atoms are fermions with spin 1/2. At low enough temperatures, they pair up and form a superfluid with complex spin textures. The study of these spin textures has revealed connections between condensed matter physics and cosmology, because the mathematical structures that describe superfluid helium-3 are similar to the structures that might describe the early universe. Spin shows up everywhere, from the smallest scales to the largest, from individual particles to bulk materials to the fabric of space-time itself. There's one more piece to this puzzle. Spin is mysterious because we can't visualize it, but it's not arbitrary. The values spin can take are restricted. Particles can have spin 0, spin 1/2, spin 1, spin 3/2, spin 2, and so on. But you don't see particles with spin 1/3 or spin 2/5. The allowed values are integers or half-integers. That's not a coincidence. It's a consequence of the rotational symmetry of space. When you rotate your coordinate system, the laws of physics don't change. That symmetry, combined with the requirements of quantum mechanics, restricts the possible values of angular momentum. Spin has to come in units of 1/2 times the reduced Planck constant. Nothing else is allowed. The universe enforces this rule at every scale. From the spin of an electron to the spin of a black hole, angular momentum is quantized. It comes in discrete lumps, and the size of those lumps is set by the Planck constant, the fundamental scale of quantum mechanics. Spin is the clearest example of quantization in the everyday world. Well, not everyday, but in the quantum world that underpins the everyday world. The electrons in your body, the protons in the atoms, the photons of light bouncing off this screen, all of them have quantized spin. All of them carry angular momentum in discrete units, and none of them are rotating in the classical sense. They just are. Spinning without spinning, angular momentum without motion. It's a feature of reality that makes no sense if you think in terms of objects and motion, but it's written into the equations of quantum mechanics and confirmed by every experiment ever performed. This is the twist, the quantum twist. Rotation at the smallest scales doesn't look like rotation. It doesn't involve anything turning, but it's still angular momentum, conserved, quantized, transferable, real. Every electron has spin, every proton, every photon, every quark. The universe at the quantum level is spinning, but not in the way we've been talking about up until now. Not motion through space, just an intrinsic property, a kind of spin baked into the particles themselves. And that spin is as fundamental to the structure of reality as mass or charge. Take it away and atoms collapse. Chemistry disappears. Matter becomes unstable. The exclusion principle vanishes. The universe as we know it ceases to exist. Spin is not optional. It's not a detail. It's a pillar holding up the entire structure of the physical world. And it's strange. Deeply, irreducibly strange. A property that behaves like rotation but isn't rotation. That can't be visualized but can be measured with exquisite precision. That obeys the same conservation laws as the spin of a galaxy, but exists in particles with no size and no moving parts. So now we've seen spin at every scale, from gas clouds light years across to black holes twisting spacetime to electrons carrying intrinsic angular momentum without moving. The rule is the same. Angular momentum is conserved, but the form it takes changes. At large scales, spin is motion, objects rotating through space. At quantum scales, spin is a property, intrinsic, permanent. Not motion, but something that behaves like motion in every measurable way. And across all those scales, from the quantum to the cosmic, the universe enforces the same rule. Spin, once present, does not disappear. It can be transferred, it can be redistributed, but it cannot be destroyed. The collapsing gas cloud that became the Milky Way had angular momentum. The galaxy inherited it. The Sun inherited it from the protoplanetary disk. Earth inherited it from the collisions that built the planet. And the electrons in your body inherited it from the quantum fields that gave birth to them in the first fraction of a second after the Big Bang. Spin is everywhere, always has been, and the universe, it turns out, does not allow stillness, not at any scale. From the largest galaxies to the smallest particles, everything is spinning, either through space or in some deeper sense written into the fabric of reality itself. Motion is not optional, it's mandatory. And the next question, the one we've been building toward, is why. Why does the universe demand motion? Why is stillness forbidden? Why, out of all the possible ways reality could have been structured, did we end up in a cosmos where everything spins? That's the question we're going to answer next. Because the spinning is not random, it's not an accident, it's a consequence of the deepest rules governing the universe. And when you follow those rules to their logical conclusion, you find that a universe without spin would be a universe that couldn't exist. We've been on a journey, from gas clouds collapsing in the dark ages of the universe to stars spinning because conservation gave them no choice. From planets inheriting that spin and holding on to it for billions of years to galaxies wheeling through space like cosmic hurricanes. From black holes rotating so fast they twist space-time into knots to electrons carrying intrinsic angular momentum without moving at all. At every scale, at every stage, the same rule applied. Angular momentum is conserved. Once the spin is there, it doesn't vanish. It can be transferred, it can be redistributed, it can change form, but it cannot be destroyed. And now we need to step back and ask the question that's been lurking beneath all of this. Why? Why is everything spinning? Why is motion the rule and stillness the exception? Why, in a universe that could in theory have been perfectly static, perfectly balanced, perfectly still, do we instead live in a cosmos where nothing ever stops moving? The answer is not that the universe happened to start with some rotation and we're just stuck with it. The answer is deeper. Stillness is not just rare, it's forbidden. Not by law in the human sense, not by decree, but by the structure of reality itself. A universe without motion would be a universe that couldn't exist, or more precisely, it would be a universe that couldn't stay existing for more than the briefest instant. Because motion is not a detail, it's not a feature you can remove and still have something resembling the cosmos we observe. Motion is load-bearing. Take it away and the entire structure collapses, literally. Let's start with the most obvious reason: gravity. Gravity is always attractive, always pulling. Every piece of matter in the universe is pulling on every other piece, trying to bring everything together into one point. If the universe were static, if nothing were moving, gravity would win immediately. Everything would collapse. Stars would fall into each other. Galaxies would crunch down into single points. The entire universe would contract under its own weight. There would be no structure, no space between things, just a single infinitely dense blob. That's not the universe we live in. We live in a universe with structure, stars separated by light years, galaxies separated by millions of light years, voids between galaxy clusters stretching across hundreds of millions of light years. All of that space, all of that separation, exists because things are moving, orbiting, spinning. The motion provides resistance. Not a force pushing outward in the traditional sense, but a tendency for moving objects to keep moving in straight lines. Inertia. An object in motion stays in motion unless something stops it, and when that motion is perpendicular to the direction gravity is pulling, you get an orbit. The object falls toward the center, but it's also moving sideways, so it keeps missing. It curves around instead of crashing in. The orbit is stable as long as the motion continues. Stop the motion, and the orbit collapses. This is not a minor detail. This is the reason solar systems exist. The reason galaxies have disks instead of collapsing into black holes. The reason you can have planets orbiting stars for billions of years without falling in. Every stable orbit in the universe is a balance between gravity pulling inward and motion carrying the object sideways. The two forces don't cancel, they combine into a curved path, a circle or an ellipse. The object is constantly falling, but the ground keeps curving away beneath it. That's an orbit, and it only works if the object is moving. If Earth stopped moving through space, stopped orbiting the Sun, gravity would pull it straight inward. Within about 64 days, Earth would crash into the Sun's surface. The same is true for every planet, every moon, every satellite, every asteroid. Stop the motion and they fall. The motion is what keeps them up. And the motion is there because angular momentum was present from the beginning, inherited from the rotating disk of gas and dust that formed the solar system. That angular momentum is conserved. It's been holding Earth in orbit for 4.5 billion years, and it will keep holding Earth in orbit for billions more unless something external disrupts it. A collision, a close pass by another star, something that transfers angular momentum away. But left alone, the orbit is permanent. Because the motion is permanent, because angular momentum cannot be destroyed, scale that up to galaxies and the same logic applies. Galaxies are not collapsing into their central black holes because the stars in the galaxy are orbiting. They have angular momentum, the galaxy as a whole is rotating, and that rotation provides centrifugal support, not a real force. Centrifugal force is a fictitious force that appears in rotating reference frames, but the effect is real. Objects moving in circles experience an outward pull in their own reference frame. That pull counteracts gravity. It keeps the stars from spiraling inward. If you could somehow stop the rotation of the Milky Way, if you could remove all the angular momentum from every star, the galaxy would collapse. The stars would fall toward the center. Within a few million years, the entire galaxy would crunch down into a supermassive black hole. The spiral structure would vanish. The disk would vanish. Everything would pile up in the middle. That's what happens when you take away the spin. The structure disappears. The galaxy ceases to exist as a galaxy. It becomes a point mass, a singularity. And the same logic extends to galaxy clusters, to superclusters, to the large-scale structure of the universe. Everything is held apart by motion, rotation, expansion. The dynamic nature of the cosmos is not incidental. It's the only thing preventing total collapse. There's a subtlety here that's easy to miss. The universe as a whole is expanding, space itself is stretching. That expansion is not rotation, it's not motion through space, it's motion of space. But the effect is similar. The expansion provides separation. It keeps galaxies from falling into each other. Without expansion, the universe would recollapse under its own gravity. That was one of the possible fates for the universe that cosmologists considered for decades. A closed universe, where gravity eventually wins and everything falls back together in a big crunch. But observations in the late 1990s showed that the expansion is accelerating. Something is pushing the universe apart faster and faster. We call that something dark energy, and we have no idea what it is. It makes up about 68% of the total energy density of the universe, and its effect is to prevent collapse on the larger scales. Dark energy provides a kind of cosmic anti-gravity, a repulsive force that grows stronger as space expands. It's not rotation, but it's serving the same function. It's keeping the universe from collapsing. Motion, expansion, acceleration, all of it is working against gravity. And gravity is relentless. It never stops pulling. So the motion, the expansion, the spin, all of it has to keep going, permanently. Because if it stops, even for a moment, gravity wins and everything collapses. Now let's talk about structure formation. The universe wasn't always full of galaxies. For the first few 100 million years after the Big Bang, there were no stars, no galaxies, just vast clouds of hydrogen and helium drifting through space. Those clouds were lumpy, slightly denser in some places, slightly less dense in others. The density fluctuations were tiny, maybe 1 part in 100,000, but they were enough. Gravity amplified them. Denser regions pulled in more gas. They grew denser. The process fed on itself. Over millions of years, the fluctuations grew into the first structures, clouds massive enough to collapse under their own weight. And when those clouds collapsed, they didn't collapse into points. They collapsed into rotating disks, because the clouds had angular momentum, just a tiny bit. But conservation of angular momentum demanded that as the clouds shrank, the rotation sped up. The clouds flattened. The material settled into orbits around the center. Stars formed in the disk. Galaxies were born. And every step of that process required rotation. Without angular momentum, the clouds would have collapsed into spherical blobs. Maybe they would have formed stars, but those stars wouldn't have organized into disks. There would be no spiral galaxies, no structure, just chaotic clumps of stars with no coordination. The beautiful spiral arms we see in galaxies like the Milky Way and Andromeda are a direct consequence of rotation. The arms are density waves propagating through the rotating disk. They exist because the galaxy is spinning. Take away the spin, and the arms disappear. The disk disappears. You're left with an elliptical blob, a spherical or football-shaped galaxy with no clear structure and no organized rotation. Elliptical galaxies exist and they're common, but they're usually the result of mergers. Two spiral galaxies collide, their disks get torn apart, and the result is an elliptical. The rotation is still there, but it's scrambled. The stars are moving in all different directions instead of orbiting in a coordinated plane. The merger destroyed the structure that rotation had built. There's a deeper point here. Rotation is not just preventing collapse, it's enabling complexity. A static universe would be simple, a blob, a point, no interesting features, no variation. But a rotating universe, a universe where different parts are moving at different speeds, where material is organized into disks and spirals and streams, that's a universe where complexity can emerge. Stars form in specific regions of the disk. Planets form in specific orbits. Some planets end up in the habitable zone, the region where temperatures are right for liquid water. Life, if it emerges in a rotating system, a planet spinning on its axis, orbiting a star which is orbiting the center of a galaxy. Every layer of motion, every rotation, contributes to the environment that makes life possible. Earth's rotation gives us day and night. The rotation mixes the atmosphere, distributes heat, drives weather patterns. Without rotation, one side of Earth would be permanently facing the sun, baking in constant heat. The other side would be in permanent darkness, frozen solid. The planet would be uninhabitable. Earth's orbit around the sun, slightly elliptical, gives us seasons. The tilt of Earth's axis, 23.5 degrees, is also a consequence of the chaotic collisions that built the planet. That tilt enhances the seasons, making some regions warm in summer and cold in winter. The variation drives biological diversity, different ecosystems adapted to different conditions, all of it tied back to motion, to rotation, to the fact that Earth is spinning and orbiting and the solar system is moving through the galaxy. A static Earth would be a dead Earth. The same logic applies at smaller scales. Inside a star, rotation affects how the star evolves. A rapidly rotating star can mix material from the core to the outer layers more efficiently than a slowly rotating star. That mixing changes the star's lifetime, its brightness, its eventual fate. Rotation also generates magnetic fields through the dynamo effect. Moving charged particles create currents, and currents create magnetic fields. The sun's magnetic field is generated by the rotation of the sun's interior, where plasma circulates in complex patterns. That magnetic field drives solar flares, coronal mass ejections, sunspots, all the dynamic activity we see on the sun's surface. Without rotation, the sun would be a static ball of fusing hydrogen, with no magnetic activity. No solar wind, no interaction with Earth's magnetosphere. The auroras, the shimmering lights near the poles caused by charged particles from the sun colliding with Earth's atmosphere, would not exist. Rotation is not optional. It's woven into every process that makes the universe dynamic and interesting. At the quantum level, the story is the same. Electrons have spin. That spin determines their magnetic moments, their behavior in atoms, their response to external fields. Without spin, atoms wouldn't have the structure they do. The Pauli exclusion principle, which says that no two fermions can occupy the same quantum state, relies on spin. Electrons in an atom fill up energy levels two at a time, one spin up and one spin down. Once a level is full, additional electrons have to go into higher levels. That's why atoms have shells. That's why chemistry works. Different elements have different numbers of electrons, and those electrons fill up the shells in specific ways. The arrangement of electrons determines how atoms bond, what molecules they form, what materials are stable. All of chemistry, all of biochemistry, all of the molecular machinery that makes life possible, rests on the fact that electrons have spin and obey the exclusion principle. Take away the spin, and you take away the exclusion principle. Electrons would all collapse into the lowest energy state. Atoms would have no structure. Chemistry would not exist. Matter would not have the properties we rely on. The universe would be a formless soup of particles with no way to organize into anything complex. Spin at the quantum level is just as essential as rotation at the cosmic level, and it's conserved by the same rule. Angular momentum cannot be created or destroyed. It can only be redistributed. The spin of an electron is permanent. The rotation of a galaxy is permanent. Both are protected by the same law. There's a philosophical angle to this that's worth considering. Angular momentum is a kind of memory, a record of the past written into the motion of the present. The rotation of the Milky Way is a memory of the gas clouds that collapsed to form it 13 billion years ago. Those clouds were rotating slowly because of tidal torques and turbulence in the early universe. That rotation has been preserved, amplified, and passed down through every generation of structure that formed since. The Sun's rotation is a memory of the protoplanetary disk. Earth's rotation is a memory of the collisions that built the planet. Even the spin of an electron is a memory of the quantum fields it was born from. The universe is a memory keeper. It does not forget motion. Once something starts spinning, it keeps spinning until something external intervenes. And because the universe is mostly empty, external intervention is rare. So the motion persists for billions of years, for trillions of years, potentially forever. The spin you see today in the Milky Way is the same spin that was there when the galaxy formed. The angular momentum has been reshuffled, transferred from gas to stars to planets to black holes, but the total amount is the same. It's conserved. And that conservation is a link connecting the present to the earliest moments of the universe's history. When you look at a spinning galaxy, you're seeing an echo of the Big Bang. The motion is ancient, primordial, and it's still here because the universe does not allow it to vanish. Now let's address the claim that shows up in some speculative papers, the idea that the universe itself might be rotating, not expanding in all directions uniformly, but spinning around some axis. If true, that would be a profound discovery. It would violate the cosmological principle, the assumption that the universe looks the same in all directions and at all locations. But the cosmological principle is an assumption, not a proven fact. It's a simplification that makes the math easier, and there have been hints, tentative, controversial, that the universe might not be perfectly isotropic. Some analyses of the cosmic microwave background, the faint glow of radiation left over from the early universe, have suggested subtle patterns that could be interpreted as evidence of rotation, a preferred axis, a direction in which the universe is spinning. If that's real, it would mean the universe has been rotating since the Big Bang, and that rotation would have seeded the angular momentum we see in galaxies today. The galaxy's spin wouldn't just be inherited from local turbulence, it would be inherited from the universe itself, a cosmic memory passed down from the very beginning. But the evidence is weak. Most cosmologists are skeptical. The patterns in the microwave background could be noise, statistical flukes. The universe could be expanding without rotating. The mainstream view is that there's no net rotation on the larger scales. The universe is homogeneous and isotropic, at least approximately, but the possibility remains open, and if future observations confirm a global rotation, we'll have to rewrite the textbooks. Again, because it would mean the universe is not just expanding, it's spinning. And everything we see, every galaxy, every star, every planet is caught up in that cosmic spin. The motion would be universal, unavoidable, written into the fabric of space-time from the first instant of the Big Bang. Even if the universe as a whole is not rotating, the principle remains. Rotation is ubiquitous. From the smallest particles to the largest structures, everything is spinning or carrying intrinsic angular momentum, and that spin is protected by conservation. There's a line in one of the research papers that captures this idea perfectly. The author wrote that cosmic rotation can possibly impart rotation to galaxies, clusters, stellar systems, and so on. The idea is that if there's any rotation at the larger scales, it propagates downward. It influences smaller structures as they form. The rotation is inherited, amplified, and preserved, and once it's there, it doesn't go away. The universe is a cascade of spin. Motion at one scale feeding into motion at the next. All of it governed by the same rule. Angular momentum is conserved. The total spin of a closed system does not change unless something external acts on it. And the universe, by definition, has no external. It's everything. So the total angular momentum of the universe, whatever it is fixed. It was set at the Big Bang, or possibly before, if the Big Bang was not the absolute beginning. And that angular momentum has been redistributed, concentrated, diluted, transformed, but never destroyed. It's still here, all of it, spread across every rotating object in the cosmos, from the spin of an electron to the rotation of a galaxy to the orbital motion of a planet around a star. Every piece of motion we see today is part of the same grand total, the universe's angular momentum budget, and the budget is balanced, permanently. There's also an energy argument. Rotation is a way to store energy, kinetic energy. A spinning object has rotational kinetic energy proportional to its moment of inertia and the square of its angular velocity. The faster it spins, the more energy it has. That energy can be converted into other forms: heat, light, gravitational waves. But as long as the object is spinning, the energy is there. and extracting that energy requires something to act on the object to slow it down. In space, there's usually nothing around to do that, so the energy stays locked in the rotation. For a long time, the Earth has been spinning for 4.5 billion years and it's only slowed down slightly. The day is a few hours longer now than it was when the planet formed. That slowdown is caused by tidal forces from the Moon, which are gradually transferring Earth's rotational energy into the Moon's orbital energy. But the process is slow. Earth will keep spinning for billions more years, and the rotational energy stored in that spin is enormous. If you could somehow tap into it, extract it, and use it, you could power civilization for a very long time. The same is true for other rotating objects. Black holes, as we discussed, are batteries. They store energy in their spin, and that energy can, in principle, be extracted through processes like the Penrose mechanism. A rotating black hole is not just a gravitational pit, it's a reservoir of usable energy. And the energy is there because the black hole inherited angular momentum from the star it formed from. The star was rotating. The core collapsed. The rotation concentrated. The black hole ended up spinning at nearly the speed of light, and all that kinetic energy is now locked in the geometry of space-time around the black hole. Waiting, available, if you have the technology to access it. Rotation is not just preventing collapse, it's also a storage mechanism, a way for the universe to keep energy in a stable, long-lasting form. And because angular momentum is conserved, that storage is secure. The energy stays where it is until something comes along to extract it. Here's where we tie it all together. Stillness is forbidden because the universe is a dynamic system. It's not a static backdrop. It's a constantly evolving, constantly moving structure governed by laws that do not allow equilibrium. Gravity pulls, motion resists, expansion stretches, dark energy accelerates. And angular momentum, once present, cannot vanish. All of these forces and rules combine to produce a cosmos where nothing ever stops. A universe at rest would be unstable. It would collapse under its own weight, or it would never have formed structure in the first place. The lumps in the early universe, the density fluctuations that eventually became galaxies, grew because gravity amplified them. But if those lumps had no angular momentum, they would have collapsed into black holes immediately. There would be no stars, no planets, no life. The fact that the lumps were rotating even slightly is what saved them. The rotation provided centrifugal support. It allowed the gas to settle into disks instead of collapsing to points. And from those disks, stars formed, planets formed, complexity emerged. The universe we see today, with all its structure and variation and beauty, exists because motion is built into the foundation. Because angular momentum was present from the beginning and has been conserved ever since. Stillness is not just rare, it's incompatible with existence. A static universe would be a dead universe, a collapsing universe, or more likely not a universe at all, just a singularity, a point. The fact that we live in a universe with structure, with space, with time to evolve and complexity to explore, is proof that stillness is forbidden. The universe has no choice but to move, and we, living inside it, have no choice but to move with it. Spinning on a rotating planet, orbiting a rotating star, inside a rotating galaxy, in a universe that has been in motion since the moment it began. And here's the unsettling part. We don't fully understand why angular momentum is conserved. We know that it is. We can prove it mathematically from the rotational symmetry of space. If the laws of physics don't change when you rotate your coordinate system, then angular momentum must be conserved. That's Noether's theorem, one of the most beautiful results in physics. But the theorem doesn't explain why space has rotational symmetry in the first place. It just says that if it does, then angular momentum is conserved. Why does space have that symmetry? Why is the universe built that way? We don't know. It's a brute fact about reality. An axiom. Something we take as given because it works. Every experiment ever performed confirms it. Angular momentum is conserved, always, without exception. But the reason, the deep underlying reason, remains a mystery. Maybe it's tied to the structure of space-time. Maybe it's a consequence of quantum mechanics. Maybe it's just the way the universe had to be in order to exist. We don't know, and that's okay. Science is full of mysteries. But this one is special, because angular momentum conservation is not a minor detail. It's the rule that makes motion permanent, that allows structure to exist, that enables complexity, that prevents collapse. It's the reason everything spins, and we don't know why it's true. We just know that it is. And the universe, in all its spinning, rotating, orbiting glory, is the proof. There's one more implication we need to address. If rotation is essential, if motion is required for structure and complexity, then the absence of motion is equivalent to the absence of everything interesting. A universe without spin would be a universe without galaxies, without stars, without planets, without chemistry, without life. Stillness is not peaceful, it's not restful, it's death, the end of structure, the collapse into simplicity. Motion is what makes the universe complex, what allows it to evolve, what gives it a history and a future. A static snapshot of the universe would be meaningless. The universe is not a photograph, it's a movie. A long, slow, billions of years long movie where every frame is slightly different from the last. And the motion, the change, the spin is what creates the narrative. Take away the motion and you take away the story. You're left with a frozen frame, a single instant with no past and no future. That's not a universe, that's a dead end. The universe we live in is alive, not literally, but dynamically. It's changing, evolving, spinning. And that spin is not optional, it's mandatory, written into the laws of physics, enforced by conservation, unavoidable, permanent. So why is stillness forbidden? Because the universe is not designed to be still. It's designed, if that's even the right word, to move. Gravity demands collapse, motion prevents it, expansion demands separation, angular momentum preserves it, dark energy accelerates it. And at every scale, from the quantum spin of an electron to the rotation of a galaxy, to the possible spin of the universe itself, motion is the rule. Stillness is the exception, the anomaly, the thing that only exists in idealized textbooks and thought experiments. In the real universe, nothing is still. Nothing has ever been still, and nothing ever will be, because the moment something stops moving, gravity takes over and the structure collapses, or quantum mechanics takes over and the particle ceases to behave the way it's supposed to, or the orbit decays and the planet falls into the star, or the galaxy stops rotating and the stars spiral into the center. Motion is not a luxury, it's a necessity. The universe could not exist without it. And because angular momentum is conserved, because the spin that was present at the Big Bang is still here today, the motion is guaranteed, permanent, unavoidable. The universe is spinning. It has always been spinning, and it will keep spinning long after the last star dies and the last black hole evaporates and the cosmos fades into a cold, dark, expanding void. Even then, in that distant future, the angular momentum will still be there, conserved, waiting. A memory of the universe that was, a record written in motion that nothing can erase. This is the grand design. Not a blueprint, not a plan, but a consequence, a logical outcome of the rules that govern reality. Angular momentum is conserved, gravity pulls, motion resists, and from those simple rules, enforced without exception across billions of years and trillions of light years, the entire spinning, rotating, orbiting, dynamic cosmos emerges. Everything moves because everything must move. Stillness is not allowed. It's forbidden by the structure of the universe itself. And that's not a flaw, it's not a problem. It's the reason we're here. The reason anything is here. The reason the universe is more than a point or a void. Motion is the foundation, rotation is the rule, and the dance, the cosmic dance of spin and orbit and expansion and contraction, is the only dance the universe knows. It's been dancing since the beginning, and it will keep dancing until the end. Because in this universe, stillness is not an option. It never was. We've climbed a ladder that stretches from the quantum foam to the edge of the observable universe. We've seen electrons carrying spin without spinning, stars igniting because collapsing clouds couldn't stop rotating, planets holding on to angular momentum for billions of years like a birthright they can't refuse. We've watched galaxies wheel through space, black holes twist space-time into knots, and we've learned that stillness, true stillness, is not just rare. It's forbidden. The universe does not allow it. Motion is written into the foundation of reality so deeply that you can't remove it without the entire structure collapsing. And now, at the end of this journey, we need to step back one more time. Not to look at another scale or another mechanism or another exotic object spinning faster than the last, but to see the whole picture, to understand what it means that we live in a universe where everything, at every scale, is in motion, where spin is not a detail, not a feature you can ignore or explain away, where rotation is the rule and stillness is the exception that proves it. This is the cosmic dance, the symphony of spin, and it's playing right now, all around you, whether you can hear it or not. Let's start with the number we've been carrying around since the beginning, 10 to the 49th kilograms times meters squared per second. That's the symbolic fingerprint, the rough estimate of the total angular momentum in the observable universe. It's not a measurement you'll find in a mainstream cosmology textbook. It's not a number that astronomers have directly observed by adding up every galaxy and every star and every black hole. It's more like a back-of-the-envelope calculation, an attempt to capture the sheer scale of motion in the cosmos. Take all the galaxies we can see, roughly 200 billion to 2 trillion of them depending on how you count. Give each one an average spin, add in the rotation of stars, planets, moons, asteroids, the spin of black holes, the angular momentum locked in accretion disks and stellar winds and interstellar gas clouds. Sum it all up and you get a number in the ballpark of 10 to the 49th, maybe a bit higher, maybe a bit lower. The exact value doesn't matter. What matters is the scale, the enormity, the fact that the universe contains enough rotational motion to make that number meaningful. And that number is conserved. Every bit of angular momentum in the universe today was there at the Big Bang, or it was generated in the first moments afterward and has been preserved ever since. The universe is not creating new spin, it's redistributing the spin it started with, concentrating it in some places, spreading it out in others, but the total, the grand sum, stays the same. That's conservation. And it's one of the most powerful rules in physics. Angular momentum cannot be created, it cannot be destroyed, it can only be moved around. And the fact that the observable universe has this much angular momentum, this colossal budget of spin spread across every structure we can detect, tells us something profound. The universe is not static. It never was. It was born in motion, and it will stay in motion until the end. Now let's talk about what the mainstream actually says, because this is where we need to be careful. The idea that the entire universe, as a single entity, is rotating around some cosmic axis is controversial. Most cosmologists do not believe it. Observations of the cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old, show no evidence of a preferred direction, no axis of spin. The universe, at the largest scales we can measure, appears to be isotropic. It looks the same in all directions, and that isotropy is one of the pillars of modern cosmology. If the universe was spinning, we'd expect to see a pattern in the microwave background, a directional signal, some indication that one part of the sky is different from another in a systematic way. We don't see that, or at least we haven't seen it convincingly. There have been hints. A few analyses have suggested subtle patterns that could maybe be interpreted as evidence of rotation. But the signals are weak, right at the edge of detectability, and most researchers think they're more likely to be noise or systematic errors than real cosmic spin. So the conservative, widely accepted position is that the universe as a whole has no net rotation. It's expanding uniformly in all directions. No spin, no twist, just expansion. But, and this is the critical point, that does not mean nothing in the universe is spinning. It means the opposite. The universe is not rotating as a single object, but almost everything inside the universe is rotating. Galaxies spin, stars spin, planets spin, black holes spin, even particles have intrinsic angular momentum. The universe is full of spin. It's just not organized into a single grand rotation. The motion is local, distributed. Each structure spinning on its own, governed by the angular momentum it inherited from the cloud of gas that formed it. The universe is not a spinning top. It's a swarm of spinning tops, billions and trillions of them, each doing its own thing, but all of them, every single one obeying the same rule. Angular momentum is conserved, and that leads to the interconnectedness. Because even though each galaxy is spinning independently, even though each star and planet and black hole has its own angular momentum, none of them exist in isolation. They interact, gravitationally, magnetically, through radiation and tidal forces and the occasional collision, and every interaction transfers angular momentum. A star passes near another star, and the gravitational tug between them changes both their orbits. A moon orbits a planet and tidal forces slow the planet's rotation while pushing the moon farther away. A black hole tears apart a passing star, and the debris forms an accretion disk, inheriting the angular momentum from the star's original orbit. Two galaxies collide and their angular momentum vectors add, producing a new galaxy with a spin that's the sum of the two originals, though scrambled and redistributed. The universe is not a collection of isolated systems, it's a network, a web of interconnected spins constantly exchanging angular momentum, constantly influencing each other, and because the total angular momentum is conserved, every transfer is balanced. If one object gains spin, another loses it. The books always balance. The universe keeps perfect accounting. And that interconnectedness is what gives the cosmos its structure. If everything were truly isolated, if angular momentum couldn't be transferred, the universe would be a very different place. But it's not isolated, it's connected. And the connections, the gravitational threads linking every object to every other object, create the large-scale structure we see, the cosmic web, the filaments of galaxies stretching across hundreds of millions of light years, the clusters and superclusters and voids, all of it shaped by gravity, and all of it, at some level, influenced by the spin of the components, because spin affects how structures form, how they collapse, how they interact. A rotating cloud collapses into a disk. A non-rotating cloud collapses into a sphere. The difference is angular momentum, and that difference determines whether you get a spiral galaxy or an elliptical galaxy, whether you get a solar system with planets in a flat plane or a chaotic cluster of stars with no organization. Spin is not just motion, it's structure. It's the reason the universe has the diversity it does, the variety, the complexity. Take away the spin and you take away the structure. You're left with a featureless blob, a universe of spherical clouds with no interesting features. But we don't live in that universe. We live in a universe where rotation is ubiquitous, and that rotation is what makes everything interesting. Now let's talk about evolution. Cosmic evolution. The idea that the universe changes over time, that it has a history, that it's not the same now as it was 10 billion years ago. The universe started simple. A hot, dense fog of hydrogen and helium. No stars, no galaxies, no structure, just gas expanding and cooling. Over hundreds of millions of years, that gas clumped together under gravity. The clumps collapsed into the first stars. The stars clustered into the first galaxies. The galaxies merged into larger galaxies, and at every step, rotation played a role. The clumps that became galaxies were rotating, slowly at first, then faster as they collapsed. The rotation determined the shape of the galaxy, disk or blob, spiral or elliptical. The stars that formed inside the galaxies inherited the galaxy's rotation. They orbited the center in coordinated patterns. Planets formed around the stars, also inheriting the rotation. And life, when it emerged on rotating planets. Planets with day and night cycles, seasons, weather driven by atmospheric circulation caused by rotation. Every step of that evolution was shaped by spin. Without rotation, the gas clouds wouldn't have formed disks. Stars might have formed, but they wouldn't have organized into galaxies with structure. Planets wouldn't have formed in stable orbits. And life, if it emerged at all, would have faced a very different environment. A static planet with one side always facing the sun. No day-night cycle, no mixing of the atmosphere, no seasons. The conditions for life as we know it depend on rotation. Earth's rotation, Earth's orbit, the solar system's motion through the galaxy, all of it contributes to the environment that makes biology possible. And all of it traces back to angular momentum, inherited from the protoplanetary disk, inherited from the molecular cloud that collapsed to form the sun, inherited from the turbulence in the early universe. The spin is ancient, and it's still here, driving the evolution of the cosmos, enabling complexity, making the universe a place where interesting things can happen. And here's where it gets really interesting. The diversity we see in the universe, the sheer variety of structures and objects and phenomena, is a direct consequence of rotation. Not just that things rotate, but that they rotate at different rates and in different directions and with different amounts of angular momentum. Earth rotates once every 24 hours. Jupiter rotates once every 10 hours. Venus rotates once every 243 days, and it rotates backward. Each planet has a different spin because each planet formed through a different sequence of collisions and interactions. The chaos of the early solar system left its mark on the final spins. The same is true for stars. Some stars rotate rapidly, once every few hours. Others rotate slowly, once every few months. The difference depends on the star's mass, its age, and its history. Young stars rotate faster than old stars because they haven't had time to spin down through magnetic braking. Massive stars rotate faster than small stars because they inherited more angular momentum from the collapsing cloud. And black holes, the extreme case, can rotate at nearly the speed of light if they formed from a rapidly rotating star, or if they've been spun up by accreting matter from a companion. Every object has its own spin, its own angular momentum, and that diversity is what makes the universe dynamic. If everything rotated at the same rate, the universe would be boring, predictable. But it's not. Every galaxy is different. Every star is different. Every planet is different. And the differences are encoded in the spin. How fast, how tilted, how much angular momentum. Those details determine the object's evolution, its lifetime, its interactions with other objects. Spin is not just a number, it's a biography, a record of where the object came from and what happened to it along the way. And because angular momentum is conserved, that record is permanent. You can read the history of a galaxy by measuring its rotation. You can read the history of a planet by measuring its spin and its orbit. The motion is a memory, a fingerprint, and it's written in a language that the universe never forgets. Now let's address the mysteries, because for all we've learned about spin, for all the observations and the equations and the experiments, there are still deep questions we can't answer. The first mystery is dark matter. We know it's there. We know it outweighs ordinary matter by a factor of 5 or 6 to 1. And we know it has angular momentum. Dark matter halos around galaxies are rotating. We can infer that from the rotation curves of the galaxies themselves. But we don't know what dark matter is. We don't know if it's made of particles, and if so, what kind. We don't know if dark matter particles have spin in the quantum sense. Do they obey the Pauli exclusion principle like electrons and protons? Or do they behave like bosons, piling on top of each other in the same quantum state? The answer would tell us a lot about how dark matter clumps and how it interacts with ordinary matter, and it would affect the formation of galaxies and the evolution of structure on the larger scales. Right now, we don't know. Dark matter is a mystery with spin written into it, and until we detect a dark matter particle directly, measure its properties, figure out what it is, the mystery remains. The second mystery is primordial spin alignment. Some observations suggest that galaxies in the same region of space tend to have their spin axes aligned. Not perfectly, but more aligned than you'd expect from random chance. If that's real, it's a hint that something in the early universe was organizing the spin. Tidal torques from neighboring structures could do it. Or maybe there was some kind of a large-scale flow in the primordial gas that imprinted a preferred direction. Or maybe, and this is the really speculative idea, the universe itself had a tiny bit of rotation that got amplified as structure formed. We don't know. The observations are tantalizing but not conclusive, and the theory is still being worked out. If galaxies really do have aligned spins on large scales, it would tell us something profound about the conditions in the early universe, about how structure formed, about whether the universe was perfectly symmetric, or whether there were subtle asymmetries that left their mark on everything that came after. The third mystery is the connection between quantum spin and cosmic spin. We've talked about both. Electrons have intrinsic angular momentum. Galaxies have rotational angular momentum. Both are measured in the same units. Both obey the same conservation law. But they're different. Quantum spin is not motion. It's a property, an eigenvalue of a quantum operator. Cosmic spin is motion, objects physically rotating through space, and yet the math treats them the same way. Angular momentum is angular momentum. Add the quantum spin of all the particles in a galaxy to the orbital angular momentum of all the stars and you get the total angular momentum of the system. The universe doesn't care whether the angular momentum comes from quantum particles or rotating clouds. It's all the same. But why? Why is there this deep connection between the quantum world and the classical world? Why does spin at the smallest scales obey the same rules as spin at the larger scales? The answer, as far as we can tell, is that angular momentum conservation is a fundamental symmetry of the universe. It's not an accident. It's not a coincidence. It's a consequence of the fact that the laws of physics don't change when you rotate your coordinate system. That symmetry, called rotational invariance, is baked into the structure of reality. And from that symmetry, through a mathematical result called Noether's theorem, angular momentum conservation follows automatically. The conservation law is not imposed from outside. It's derived from the symmetry. The universe has rotational symmetry, so angular momentum must be conserved. But that still doesn't explain why the universe has rotational symmetry in the first place. That's a deeper question. A question about the nature of space and time and why they have the properties they do. And we don't have an answer. We just know that the symmetry is there. And because it's there, angular momentum is conserved. And because angular momentum is conserved, spin is permanent. The connection between quantum spin and cosmic spin is a reflection of that deep underlying symmetry, a hint that the universe, at its core, is more unified than it appears, that the rules governing the smallest particles are the same rules governing the largest structures, that there's a continuity, a thread running from the quantum to the cosmic, and spin is one of the places where that thread is most visible. There's also the question of what happens in the far future. The universe is expanding, accelerating, driven by dark energy, the mysterious force that makes up about 68% of the total energy density of the cosmos. As the expansion continues, galaxies will drift apart. The space between them will grow. Eventually, billions of years from now, the galaxies outside our local group will be so far away that their light will be redshifted beyond detectability. The observable universe will shrink. The Milky Way and Andromeda will have merged by then, forming a large elliptical galaxy. The stars inside that galaxy will keep orbiting. The black hole at the centre will keep spinning. But the galaxy will be alone. No neighbours, no interactions, just a single island of light in an expanding void. And even that won't last. Stars will burn out, one by one. The universe will run out of gas to form new stars. The last stars will die. The galaxies will go dark. All that will be left are black holes, and the black holes will evaporate. Slowly. Through Hawking radiation. A process so slow that it takes 10 to the power of 100 years or more for a solar mass black hole to disappear completely. Supermassive black holes will take even longer, but eventually they'll evaporate too. And when the last black hole evaporates, what happens to its angular momentum? The black hole was spinning. It had angular momentum locked in the geometry of space-time around it. Where does that angular momentum go when the black hole is gone? The answer is that it radiates away. Hawking radiation carries energy and angular momentum. As the black hole shrinks, it spins down. The angular momentum is transferred to the radiation, and the radiation spreads out into the universe, carrying the spin with it. By the time the black hole is gone, the angular momentum is dispersed across an enormous volume of space, diluted, but still there, still conserved. The universe at the end, trillions and trillions of years from now, will be cold, dark and empty. But it will still contain angular momentum, somewhere, in the quantum fluctuations of empty space, in the faint remnants of the last particles, in the gravitational waves still propagating through the void. The spin will be there, because the universe cannot destroy it. It can only spread it out until it's so diluted that it becomes undetectable. But the total, the grand sum, will still equal the number it started with, 10 to the 49th kilograms meters squared per second, or whatever the actual value is. The universe's angular momentum budget balanced at the Big Bang will still be balanced at the end. The books never close, they just get harder to read, and that brings us to the holistic view. The universe is not a collection of separate objects, it's a system, a vast interconnected dynamic system where everything is in motion and everything is connected. The spin of an electron affects the structure of an atom. The structure of an atom determines the chemistry of a molecule. The chemistry of a molecule determines the behavior of a material. The material forms a planet. The planet orbits a star. The star orbits a galaxy. The galaxy interacts with other galaxies, and all of it, every layer, every scale, is governed by the same rules. Gravity, electromagnetism, conservation laws, angular momentum is conserved, energy is conserved, momentum is conserved. These are not suggestions, they're constraints. The universe is required to obey them. And the result is a cosmos where nothing happens in isolation. Everything is part of the whole. Every spin is connected to every other spin through the web of interactions that link matter and energy across space and time. The universe is a symphony, not in the poetic hand-waving sense, in the literal sense. A symphony is a coordinated arrangement of different instruments playing different notes at different times, but all following the same score. The universe is the same. Different objects spinning at different rates in different directions, but all obeying the same laws, all part of the same grand structure. And the score, the set of rules that governs the symphony, is physics. The laws of motion, the conservation laws, the symmetries. Those rules are what make the symphony coherent, what turn random motion into organized structure, what allow complexity to emerge from simplicity. Without the rules, the universe would be chaos, random particles moving in random directions with no pattern and no structure. But the rules are there, and because they're there, the chaos organizes itself. Particles clump into atoms, atoms form molecules, molecules form planets, planets orbit stars, stars cluster into galaxies, galaxies form the cosmic web, and at every step angular momentum is conserved. The spin is passed down, from the Big Bang to the present, from the largest scales to the smallest, a continuous thread linking every spinning object in the universe. Past, present, and future, all connected, all part of the same dance, and the dance is not optional. That's the part we keep coming back to. Stillness is not a choice the universe can make. Motion is mandatory, because gravity is always pulling, because empty space is unstable, because quantum mechanics forbids particles from having zero momentum, because angular momentum once present cannot be destroyed. The universe is required to move, and the motion is not random. It's organized by conservation laws and symmetry, and the structure of space-time itself. The universe is a machine, not a designed machine, not a machine with a purpose, but a machine in the sense that it has moving parts, and those parts interact in predictable ways according to fixed rules. And the output of the machine, the result of all those interactions over billions of years, is the cosmos we see. Galaxies, stars, planets, life. All of it built from motion, all of it enabled by spin, and all of it temporary, because the universe is evolving. It's not in equilibrium, it's moving toward something, not toward a goal, not toward a purpose, just toward the natural end state determined by the laws of thermodynamics and the expansion of space. The universe will eventually run down, the stars will die, the black holes will evaporate, the expansion will continue until the universe is so large and so empty that nothing interesting can ever happen again. But even then, even in that far future, the angular momentum will still be there, conserved, diluted but not destroyed, a memory of the universe that was, a fingerprint written in motion that nothing can erase. So what does it mean that we live in a spinning universe? What does it mean that everything, at every scale, is in motion? What does it mean that rotation is not a detail but a foundation? It means the universe is alive, not literally, not in the sense of being conscious or intentional, but alive in the sense of being dynamic, changing, evolving, never still, never static, always moving. And that motion is what makes everything possible. The diversity, the complexity, the structure, the chemistry, the biology, all of it depends on rotation, on the fact that angular momentum is conserved and that the universe started with enough spin to keep everything moving for billions of years. We are living inside the consequences of that initial spin. The galaxy we're in is rotating. The star we orbit is rotating. The planet we stand on is rotating. And the atoms in our bodies, the electrons orbiting the nuclei, have quantum spin that's just as real and just as conserved as the rotation of the galaxy. We are part of the dance, not observers watching from the outside, participants. Every breath you take, every heartbeat, every thought is happening inside a rotating system. You're spinning right now, at 1,000 miles per hour because Earth is spinning, at 67,000 miles per hour because Earth is orbiting the Sun, at 500,000 miles per hour because the Sun is orbiting the galaxy, and you don't feel any of it because everything around you is moving at the same speed, but the motion is there, real, measurable, permanent, and it's the reason you exist. Because without rotation, the solar system wouldn't have formed. Without rotation, Earth wouldn't have a day-night cycle. Without rotation, the conditions for life wouldn't be right. You are a product of spin, a consequence of angular momentum conservation, a pattern of atoms held together by forces that ultimately trace back to the same rules that make galaxies rotate. You are part of the cosmos, not separate from it, not immune to its rules, part of it. And the cosmos in turn is part of you. The iron in your blood was forged in a dying star. The oxygen in your lungs was created by nuclear fusion. The carbon in your DNA was assembled in the core of a massive star that exploded billions of years ago. You are made of stardust, literally, and the stars that made you were spinning. The gas clouds they formed from were spinning. The galaxy that contains those clouds is spinning. The angular momentum is there. In the atoms, in the molecules, in the structure of your body, you are a spinning thing, made of spinning things, living on a spinning planet, orbiting a spinning star, inside a spinning galaxy. And the spin, the motion, the angular momentum is what connects you to the rest of the universe. You're not separate, you're not isolated. You're part of the grand structure, part of the cosmic dance. And the dance has been going on for 13.8 billion years. And it will keep going long after you're gone, because the universe does not stop. It cannot stop. Motion is written into the foundation, and the motion, the spin, the angular momentum is the thread that connects everything. From the smallest particle to the largest galaxy, from the Big Bang to the present to the far future, all of it spinning, all of it connected, all of it part of the same grand symphony, the symphony of spin. And the number 10 to the 49th kilograms meters squared per second is the signature, the fingerprint, the measure of how much motion the universe contains. It's a big number, almost incomprehensibly big, but it's finite. It's a specific value, and that value is conserved. The universe is not creating new spin. It's not destroying old spin. It's just redistributing the spin it started with. And that redistribution, that constant shuffling of angular momentum from one object to another, from one scale to another, is what makes the universe dynamic. What keeps it interesting. What prevents it from collapsing into a static blob or a featureless void. The universe is a balancing act. Gravity pulling inward, motion pushing outward, expansion stretching space, dark energy accelerating the expansion, and angular momentum conserved at every step, tying it all together. The universe is not random. It's not chaotic. It's organized, structured, governed by rules. And one of those rules, one of the most important, is that angular momentum is conserved. The spin is permanent, the motion is permanent, and the dance, the cosmic dance of rotation and orbit and expansion and contraction, is the only dance the universe knows. It's been dancing since the beginning, and it will keep dancing until the end, because in this universe, stillness is forbidden. Motion is mandatory, and spin is not just a feature, it's the essence, the heartbeat, the rhythm that keeps the cosmos alive. Everything spins, everything moves, and everything, from the smallest electron to the largest galaxy, is connected by the same rule, the same law, the same thread of conserved angular momentum stretching across space and time. This is the cosmic dance, the symphony of spin. And you, sitting here reading this, breathing, thinking, are part of it. You always have been. You always will be. Because the universe is spinning, and so are you. You're spinning right now, 1,000 miles per hour. You've been your entire life. And you didn't choose to. You inherited it. From the planet. Which inherited it from the protoplanetary disk. Which inherited it from the molecular cloud that collapsed to form the solar system. Which inherited it from the turbulence in the early universe. Which inherited it from the Big Bang. Or maybe from something before that. We don't know. But the spin is there. It's always been there. And it's not going away. Because the universe has a rule. One of the oldest rules. One of the most unbreakable. Angular momentum is conserved. You can move it around. You can transfer it from one object to another. You can concentrate it or spread it out. But you cannot destroy it. And you cannot create it from nothing. The total spin of the universe, whatever it is, was set at the beginning. And it's still here. All of it. Locked into every rotating object. Every galaxy. Every star. Every planet. Every electron. The motion is ancient, primordial, and it's the reason anything exists, because a static universe would collapse under its own weight. A universe without spin would have no structure, no galaxies, no stars, no planets, no chemistry, no life. Stillness is not peaceful, it's not neutral, it's death, the absence of everything interesting. Motion is what makes the universe complex, what allows it to evolve, what gives it a past and a future, and the motion is permanent. Because conservation doesn't bend, it doesn't make exceptions, it's enforced at every scale, from the spin of an electron to the rotation of a supermassive black hole, from collapsing gas clouds in the cosmic dark ages to the chair you're sitting in right now. The thread is unbroken. The angular momentum you carry in your body, in the atoms that make you, in the planet beneath your feet, connects you to the Big Bang, to the first structures, to the birth of galaxies. You are not separate from the cosmos, you are part of it, made of it. And like everything else in the universe, you're spinning. You always have been, and you always will be. Because in this universe, motion is not optional. It's the foundation, and stillness was never an option. It never will be. The next time you watch the night sky, remember that behind each point of light may lie a hidden rotation, carrying a story billions of years old.